So we are live now.
Audio is not start video. Audio. Right.
Full screen.
कर रहे हैं, हो रहा है.
Good. We are ready to go ahead.
मी तुमचा मोबाईल बंद करून नसतो.
मोबाईल बंद करून ठेवा.
बंद केलं आणि इथे ठेवतो.
पण ते काय होतं, कधी कधी तेच कॉन्टॅक्ट करतात ना मला.
हे देखो तुम्हाला तुमको यू वांट टू हैव द केक एंड
ते काय करायचं, म्यूट करून ठेवायचं.
मग तुम्हाला कळेल ना सर मी काय करायचं.
ते लाईट येतं ना.
इस पे टीचिंग डालना चाहिए था. वही क्या देखो ध्यान नहीं दिया. ये सब वर्किंग इन इंडस्ट्री एंड देन टीचिंग आल्सो ऐसा है.
तो स्टार्ट करना.
हाँ मैडम को पूछते हैं ना, मैडम रेडी है तो.
Yes, I'm ready.
You are ready, ma'am?
Yes,
so
I'm
I
ready.
think okay, we will start. PM, ma'am, go ahead.
Participants are there.
Yeah, whatever. We will start.
Good morning all. Good morning and welcome for the 5th day of the AICT sponsored STTP on real estate design using guidance tool. Myself Priya Deshpande, working as assistant professor in S.P.I.T college. Welcome for the Dr. Shaila Subbaraman. She's a very great personality. She's a retired professor from Walton College of Engineering. Dr. Shaila obtained her MTech from IISc Bangalore in 75. She has done her PhD in radiation and hot carrier effects in submicron MOS devices from IIT Bombay in 1999. Walton College of Engineering, Sangli from 1989. She worked as a resource person for various workshops, STTPs, guest lectures, expert lectures on NBA, NAC, and OBA guidelines at various colleges in Maharashtra. She was deputed by NPIU for delivering guidelines on NBA and OB. She was working as an institute, NBA, NAC coordinator, head of department, and dean academics at Walton College of Engineering, Sangli. She had industry experience in various capacities as an engineer, senior engineer, deputy manager for 14 years in semiconductor devices, IC manufacturing industries in Pune. Her areas of research interest are CMOS VLSI design, analog VLSI design, digital system engineering, DSP VLSI, testing and testability. Thank you for accepting our invitation for giving a talk on topic of high-speed digital design with low power approach. I request you, ma'am, to start your session. Okay. Kindly share my screen.
Shared, madam, already shared.
I'm not able to see that.
No, just see share again, once again. It's there.
Yes, it's there. Okay. Okay. Good morning to everybody. Sir, audio is clear?
Yes, ma'am. Please go ahead.
Okay. Welcome to my presentation in this STTP on high-speed digital system considerations in the first session, and then later on, if time permits, on synchronization and synchronizers. Let me first thank Professor Rathod sir, his team, and S.P.I.T for inviting me for this STTP
for, giving me an opportunity to interact with you all who are interested in the VLSI design. Now, last 3 days, you had exposure mostly to the design at device level. That is mostly the exposure by the lectures were on microelectronics, except Ame, who gave a very good, picture of what exactly is happening at present and what is the scope as such for us to continue working in this area. No doubt, the EDA gate level, exposure also you had to Vivado and through Cadence Incisive. Low power VLSI also you have seen yesterday. So I'm making slightly change. I'm not going to the device level low power, which was basically discussed yesterday by IIT Roorkee professor. But instead, I will be, if time permits, again, I say, I'll go for the second presentation, which is very, very important in high-speed design, is how do you synchronize the two signals when they are coming to the D flip-flop, because it's one of the important component in the sequential designs. So we know that a lot of
मॅडम मॅडम
yes,
मॅडम
sir, yes.
मॅडम तुमची स्क्रीन शेअर झालेली नाही बहुतेक.
झालेली नाही अजूनही मी इंट्रोडक्शन वरच आहे सर.
अच्छा ओके यू नॉट शेअर द स्क्रीन. ओके इट्स फाईन. ओके मॅडम.
शेअर झाली नाहीये स्क्रीन आता.
नाही दॅट्स व्हॉट आय एम सेइंग.
आता
त्याला स्क्रीन शेअर मधनं परत काढा ना एक वेळा.
ओके
डू इट वन्स.
ओके सर. ओके
आता येते. नाउ इट इज कमिंग.
ओके सर. ओके
जस्ट मिनिट लेट मी सी. आणि याला फुल स्क्रीन करून टाका मॅडम F5.
हो करते. ओके नाउ
इट इज ओके फाईन. या प्लीज गो अहेड मॅम.
Okay, sir. So what we have seen, the present technology has given to even 3 nanometers. That's what we heard from Ame as such. Now, when we are trying to basically reduce the dimensions of the devices, no doubt, the propagation delays of the devices reduce. But now we also know that when you are having such a huge compact integration of large number of transistors in a chip in smaller area, they become close to each other. And the metallization also goes to more than even 8 layers. And if you consider the interconnect from the output of one block to the input of the other block, or from the output of one gate to the input of the other gate, may be quite long. And interconnect delays are basically which is hampering the speed as such. So most of my discussion here in the part first will be based on how do we control that interconnect delay, what are the problems with the interconnect, and how signal integrity is important in high-speed design. So let us, I organize this into 3 parts as such, where part A is why do we have to consider high-speed digital design and what are the basics in that. Part B will deal with the signal integrity, initially with over an individual wire, only one interconnect. And as we know now, 64-bit processors we are working with, so there is going to be 32-bit data, 64-bit data and all that. So we have to basically see these effects or a bundle of wires. So that will be the next part as such. And then we'll consider that how basically we can control all these, this signal integrity on that. So basically, when you consider signal integrity, there is going to be one aggressor line. Aggressor line, it means on which the transition takes place, the switching takes place. And the nearby line which gets affected because of this switching is the victim line. And basically, both will be capacitively as well as inductively coupled. We are not only considering the on-chip lines, we are considering the lines on the PCB. Also, we are considering PCB to PCB. So it is a system design. So inductive effect do come into picture. And then what is the crosstalk voltage which causes the noise, and how the signal gets corrupted, and the logic level which is transmitted at one output may not reach the receiver, as the logic one may get corrupted or may go into the metastability. So, these are the problems I would like to discuss and share with you from whatever I know. So let us consider the part A, which is the considerations for high-speed design. Now, today's world we know is a digital world. We have witnessed a shift from analog radio to digital radio, analog watch to digital watch, analog-based TV to digital TV, analog computer to digital computer, analog communication to digital communication, time domain to frequency domain, and at instrument level from oscilloscope to spectrum analyzer. So everything is digital, and we know that we are also living in an area where the aim is to have everything digital. So, I mean, when we consider, then the other thing is that is digital is basically the drive. Why? Because there are the expectations from the customers. What customers want? They want that your systems, which are portable, should work with a battery and consume low power, so you do not have to charge the battery every day. It should have a real-time application. That means if some cricket match is taking place somewhere, you should be in a position to watch it immediately at your place. So you are up, in time with them. Of course, portable, because you would like to carry it in your pockets. So it has to be small in size. Low cost, obviously, this is one of the things which common man will always say, that technically everything is okay, but whether it is economical, I cannot afford it. So low cost is another factor, which after the technical specifications will come into picture, how you can optimize the cost of that. Of course, reliability is one of the very, very important thing, and the design has to be robust. The other day, we have seen this PVT corners testing. That is, how do we stretch your designs to the worst and the best, and the combinations of that as far as process is concerned, temperature is concerned, and voltage is concerned. And then even then, if it works, then it is reliable. Such EDA tools are available luckily today, and we can do it by simulation, sitting in one corner of the world, which will get manufactured at foundry level, and you will have full confidence that when it gets implemented, yes, definitely it will work. So this concept, here the testing, testability, reliability tests come into picture. Wireless operation, it has to be, because we will not be always connected to the power. So you would like to work on batteries, and there has to be connection to the internet. So wireless operation has to be there. And in the conference which took place last week, which was RAIDS 2020, it has been said that within 1,000 days, that Reliance is going to provide that within 1,000 days, all parts of India, including the remote villages also, will have the fiber net. Now, today also, yesterday also, I faced the problem. I feel that government should try on making whatever available nets are there strong, and then work on this. But it's a good initiative that we are working on that, and such problems, I think, in future, maybe 1 year down the line, may not come. So wireless operation has to be there. That is the customer requirement. We also see that when online teaching is going on, how we face the problems. It should have more user-friendly interfaces as such, so that any common person can use that. These are the expectations from the customers. So how we are going to meet these expectations? There is only the solution is that in the digital era, we have to go for designing and developing and implementing high speed besides low power digital circuits. This part will be on high speed. So as this, we have seen that this is the global, that we have gone to 3 nanometer, the voltages have gone down, high integration is there, the complete system is on the chip. Their clock is a global, because though we are talking about the synchronous and asynchronous as the two types of the design methodologies, 95% of the sequential designs are using synchronous, where clock is one of the important input as such, and the frequencies are going to gigahertz, because we are in G5 area. So do digital circuits behave as expected at high frequency? These digital circuits, what we build, behave as digital circuits up to 100 megahertz, not above that. If we go above that frequencies, then it is surprising to know, for all of you perhaps, that they start behaving like analog circuits. That is, this range is above gigahertz and above, which basically is the frequency range as on today of our requirement. What happens at those frequencies? Electrical and magnetic field effects start coming into picture. Interconnects play an important role in deciding the base, not the device. The device is scaling down. We are basically having a large research in that, and also the progress has been made. But the interconnects remain, what you can say, a hurdle in really deciding at what frequency your circuit, the devices in the chip, the blocks, on the PCBs, PCB to PCB connections. Basically, this depends upon what the interconnect material is, in which media they are working, what is the velocity of the signal passing over that, and whether you can meet whatever you want as the critical time requirement. So digital circuits do not behave as expected at high frequencies. So then what we have to consider that we have, before going to the what the problem can come, let me try to, though you are fully aware of that, just to rebrush, and which is important from high-speed digital design point of view, let me cover some basics. I'll cover, fast, we'll not go into details. When we say high frequency designs, definitely, as we have said, clock is one of the input, and it's a gigahertz, and it is clock, it means it's a square wave, making a transition from 0 to 1 and 1 to 0. Now, whether this square wave is the naturally generated or created by us, whether it is generally sine wave is called as the God wave, is called as the divine wave. So this is a fundamental, and all other waves are basically derived from the superposition of the sine waves. So when we consider square wave, ideal square wave with 50% duty cycle, it is the superposition of odd harmonic sine waves, because we have always a sine 2 pi n, and hence when n basically is 2, 0, 2, 4, this will come to 0, and only the odd components will give us the sine value, and hence there's a odd, superposition of odd harmonic sine waves. So here if you see, that this is the fundamental sine wave, let me say, of frequency, it is 10 nanoseconds, then it is 100 megahertz. This basically is the third harmonic, that is 300 megahertz, and this is the fifth harmonic, that yellow one is the fifth harmonic, 500 megahertz. And what you are trying to see is that the amplitude of the fundamental, that is first harmonic, is highest, whereas it goes on decreasing as you go to the third, fifth, seventh, and all that. And if you superimpose these sine waves of odd harmonics, then you can get a square waveform, and this square form will be very good if at all you add up many harmonics, maybe up to 17, 21, like that. And however, you cannot get away with this rise time, and this rise time plays a very important part as far as our bandwidth requirements are concerned. So we'll come to that aspect. So first of all, we should know that square wave is not something which is generated as it is. Basically, it is a superposition of the sine waves from theory point of view. You have the instruments to generate all those things. That is another point. So if we consider now in the time domain, what is the square wave? We have seen this is the waveform. Now it is on a microsecond scale. If you consider it on a nanoscale, you will see the rise time and the fall time for this. If you take the frequency spectrum of that, it will be something like this, where you can say these are all the odd harmonics with amplitude going on decreasing as the higher harmonic comes into picture. But 1 megahertz fundamental frequency can go up to 10 gigahertz also, and some high frequency component will be contributing it to form your square wave. It means high frequency components are present there. No doubt the amplitude of that high frequency or component inversely depends upon what that number is, so it goes on decreasing. So this basically is the frequency component of that. So even though high frequency components drop off rapidly, every one is critically important to recreate the 0 picosecond rise time. That is, the rise time will go on decreasing as you go on superimposing more and more odd harmonic components into that. So if we do not want such a short time, then it's okay. But rise time and bandwidth are basically related. Now choose some n, let me say it is n, 17, and consider the amplitude of all odd harmonics above 17 as 0. That is, we are basically neglecting all the odd harmonics which are above 17, and trying to recreate the time domain waveform from this equation, a sine omega t is equal to a sine 2 pi t by t, and considering the frequency, that is 1, 3, 5, you can put this period as such, or 2 pi ft, put that frequency and try to get the amplitude and plot it, and you get it like this. I consider n equal to 1, n equal to 3, n equal to 17, n equal to 19. Anything in between that will be here coming in between these assignment. And this basically is limited only up to 120 or 150 nanoseconds based on, because we would like to see what is the rise time as such. And what you can see is that for the fundamental, the rise time is very large, 10% to 90%. It goes on decreasing as you go to the higher and higher harmonic. That means and when you superimpose this, then you can get something like this, if you have, and that is the rise time we talk about. And this rise time is basically is because of the superposition of the odd harmonics, higher order harmonics as such. So highest, what is the bandwidth? Now we are basically wanted correlate rise time with the bandwidth. So let us see what is the bandwidth. I think all of you are aware of this. I need not go into the details, but it is the highest sine wave frequency component significant in a signal. So this is basically a figure of merit of a signal. Now, high-frequency digital system designs are limited by the bandwidth of an interconnect transporting the signal. I want to again emphasize the fact in the minds of the participant that it is the interconnect which basically is the culprit in restricting the frequency that you can apply or can design. So this relates, as we have said, to the components like, as I have said, the digital circuits start behaving as analog because their parasitic starts coming into picture. So for an interconnect, it will be RC if it is on-chip short wires, or LRC if a long chip on wires, the pin of a package, or a PCB or PCB to PCB interconnects. And hence we have to take into consideration the effect of this on the signal, how it gets attenuated as far as amplitude is concerned, and as far as the timing also is concerned, how timing margins are reduced. So this guides the design the physical and electrical parameters of the interconnect. So finally, we have to see at the silicon what is happening, but simultaneously what type of materials you are using, what are the dimensions of those interconnect wires and all that, and how these can be limited to an affordable level of the noise voltage. Now, if you consider the time and frequency domain, this basically, in all CMOS circuits, you will have load as a capacitive load. And basically the interconnect, these are coming into picture, or it could be R of a MOS device, sometimes that of PMOS transistor, sometimes that of NMOS, or the pull down and pull up networks. So this is a basically RC low pass filter as such. And we know that the response of this, and you consider the voltage across this will it's a capacitive effect, exponentially go on increasing with RC time constant, and will reach its value maybe after 10 times of RC. And we generally say that 70% or 69% is something which we call as the level which is important. Now, if we consider the same, the transfer function of this low pass filter, then it has, like we have gain bandwidth plot is something like this. And on that, we try to see this, what is minus 3 dB point. Now here, minus 3 dB point here is 10 gigahertz. It means in that square waveform of 1 gigahertz, whatever we have seen, in that it is 10 raised to 7. So it is 10 gigahertz at this one, when the highest amplitude is there. So 10 gigahertz fundamental frequency, you have 10 megahertz here, not gigahertz, 10 megahertz. We have 10 gigahertz as the minus 3 dB point. And this is the useful range for designing. We always talk that we want to design a amplifier which will again bandwidth ratio as 10 gigahertz, something like that. So this is one of the important parameter to start with in the designs. And on any design, you start with what is the design specification and then work it back towards the lower components and then blocks and as such. So again, I think I will just pose a point. I'm not going to the details. Why only we consider 3 dB point, not any other point? Why not minus 5 dB point and all that? And that I think is basically the energy content is mostly in the up to minus 3 dB. That 50% energy is contained in that, and all the frequencies above that do not have much energy and can be ignored. But many times when you want to basically design the filters with high cutoff frequency, and also you should have very good, what I say, decay. That is generally with RC, it is 10 dB per decade. But if you want more, 20 dB per decade. But if you want more than that, then you have to basically go for multi-level filters or reduce the cutoff frequency, the 3 dB frequency. So on such, when you have considered this, this one, if you consider 10% to 90%, which basically is your rise time, and try to plot it, that is bandwidth against rise time, you have something like this, a straight line governed by bandwidth in gigahertz is equal to 0.35 divided by rise time in nanoseconds. Again, I'm not going to the details of this. You can see the literature why this particular equation is coming into picture. But this is accurate only if you consider single pole RC filter. For multipole, it will be slightly different, and this 0.35 may not be that correct. But I mean, this is approximately, we can have a very good approximation. This is a thumb rule, which digital designers, even industries give. The first thumb rule there, if you see the thumb rules for digital design, the first thumb rule is that the bandwidth is related with TR through this equation as such. So, I mean, when you consider that you want rise time as fast as possible, as low as possible, then let us try to see what is the effect of slow and fast edge rates on the design assets. So consider two clocks. One is having, it's a square clock only, but this is having 2 nanoseconds as the rise time. And it is again 1 megahertz, I think 1 nanosecond, so 1 gigahertz signal. And the other one is almost 100 picosecond. You can see a sharp rise here, it's a slow rise. So this TR is higher than this. Now let us see when we basically receive this, and what is the frequency component of that. So for higher rise time, you can see that higher frequency components are almost nil, above certain. Whereas when you consider low rise, then there are the high frequency components going up to some higher gigahertz also. So high frequency components are contained in your square wave. If at all you consider rise time to be of very, very low. On the other hand, this seems to be a better picture from TR point of view, because when you receive it at the other end, if this is a green basically is the transmitted signal, a very good square wave with desired TR rise time and fall time. But when you receive it at the receiver, you can see some sort of I mean, ringing taking place, not much, but the same thing with 100 picosecond, you can see that because of the capacitive effect coming into picture or the coupling taking place here, there is a ringing at both the rising as well as the falling edge, and which could be unacceptable if this peak is above the tolerable level of the noise voltage, and then the corruption will take place. So you cannot really, though you desire to work for higher frequencies, that's our concept will be, we want higher frequencies, but the rise time will be low. It's completely wrong, and we have to have a trade-off between the rise time and the bandwidth as such. Then another aspect is there is a noise due to signal rise time. We consider the rise time of this, and if we have, let me say, a resistive, that is R and L are there, then we see that the R basically is something where we are trying to see the voltage. So this voltage across this is inversely proportional, L di by dt. So L into the current through R will be IR, and rise time is TR. So during this time, the voltage developed across the resistor will be given by this, which is inversely proportional to TR. If you consider the capacitive load and the inductive effect, CL and L, you again can see the voltage developed across the capacitance because of such type of transition switching taking place is L into 2CV by TR square. Here it is inversely proportional to the square of rise time. It means whether it is a resistive load or capacitive load, what we see is that the noise voltage which will be generated because of this switching is inversely proportional to TR in one case, square of TR in the second case. What does this mean is that if you want to limit the noise voltage, then obviously TR should be large. So increase in rise time, but this will decrease the bandwidth, and that is one of the very, very important, and the trade-off needs to be seen between them. So in short, with understanding of square waves, frequency spectrum, rise time, bandwidth consideration, what we understand it is that it is not the clock frequency, but the rise time, which is one of the culprits for determining the signal integrity. Signal integrity, it means whatever signal you have sent from the output of one block, and when it goes to the input of the next block through an interconnect, whether it is having logic 1 is detected as logic 1 or not, or whether it has got corrupted. That is signal integrity. So now we move to our main topic, which is consideration in high-speed digital designs with emphasis on signal integrity, which is part 2 and 3 of my this one. So points of concern in HSDD, that is high-speed digital design, is that miniaturization, as we have said, packing densities are going on increasing. The interconnects width also are going decreasing, as well as the spacing between the two. There are, because we are having system on chip, so you have incompatible technologies like power supply, digital circuits, analog circuits, RF modules, and in close proximity. The third is low power supply. As the scaling down has continued, we have gone from 1.8 to 1.2 to 0.9. I don't know 3 nanosecond device take how much power as such, but these supply voltages are decreasing, and then that doesn't leave the room for the noise margins, that is We had to take very great care to see that there is a completely, it is nullified. It's very difficult design aspect as such. And then when the switching takes place, there will be high power supply current, because we want to make the design to work at higher speed. So during the switching, there will be high power currents will be drawn from the supply, giving you a power dissipation. And there will be the input coming at the fast data. So data rate also, not only the clock, but the data rate also will be also high. So all these things are the points of concern for high-speed digital design. The threads here are, as we have said, the capacitive and inductive crosstalk coming into picture. There will be simultaneous switching of high number of ions, which basically the return path is one. So that high current basically on the return impedance causes a voltage which acts as a noise and again gets superimposed on the other lines which are sharing that return signal path. There are fast switching devices with high switching currents. Retaining, this is another thing which is called as the inter-symbol interference. That is basically is the previous symbol has not been stabilized on the interconnect and you try to send the next symbol. So there is a corruption and there is an inter-symbol interference. Again, this is a cause of the noise, and we'll see total noising. These are the threats. So we have to work on all. And it's a really great area of research since we are scaling down the devices and interconnects also. We have to see for the new types of the materials, dielectric materials as well as conducting materials, the medium as such, and then work on that. So it is not only the architecture level, that is, it works on a paper, but when you implement, it may not work. So let me go to the second part, which is signal integrity. Before that, let me ask the participant where the pace is okay, where the speed is okay. Rathod sir. Hello. Hello.
हा मॅडम व्यवस्थित आहे सर्व.
पेस ओके, स्पीड ओके आहे.
हा परफेक्ट आहे. म्हणजे आय एम ओके. आय डोंट नो अबाउट पार्टिसिपंट्स. दे कॅन स्पीक इफ एनीवन. यस मॅम, दे आर कमेंटिंग. यस मॅम.
ओके, ठीक आहे. सो
लिटिल स्लो मॅडम वन ऑफ द मॅडम कमेंटेड लिटिल स्लो. दैट्स इट.
Okay, ठीक है.
Go little slow. Go little slow.
Okay. If I'm little slow, I may not be able to cover everything, but I think you'll get an idea about it. I will try to give the briefs. Let us see. I mean, we have enough time. I think some afternoon time also, as we have seen from the previous lectures, can be utilized if at all you want more from me or interaction with me. Anyway, so signal integrity, we divide, as I have said, I have divided into two parts. One will consider signal integrity issue over an individual wire after the interconnect. How the signal propagates on the on-chip lines with RC as the parasitics coming into picture, off-chip lines which are with LC and LRC. How are the issues as far as the time of flight, which is the propagation delay on interconnect is concerned? Generally, we call here TOF. Sometimes it will be TPD, but TPD generally is used for the devices, whereas time of flight is used for the interconnect. Rise time, what is the signal strength amplitude wise? Whether we can take care of by using proper termination. So what are the effect of the terminations when you terminate it at the receiver side? I again call this as a transmitter receiver model, because something is driving, the other one is a load. So driver is the transmitter, whereas the load, which is a receiver, and we can basically adopt that transmitter receiver idea from analog here also for designing or interconnect. So everywhere in electronic circuit, it is a transmitter and receiver, whether you can consider it at the gate level or the block level or at the PCB level or PCB to PCB level. And there is a memory, as we have said, inter-symbol interference. There is retains of the previous symbols. Symbols again is the word used for transmitting the signal level at the 0 or 1. And some memory is retained there and corrupts the signals. Okay, so let us try to first see transmission line effects. Although all of you must be having communication as one of your specializations, and you all these things, let us try to apply those as far as our interconnects are concerned. So as I said, this is my driver, which is driving, could be anything. I'm just representing it as a driver, a generic term. And this is a load, which is a receiver here. And this is the source where it is sourcing this load. So this is the source end of the interconnect, whereas here it is going receiver, the end it is a destination, and this is the medium of transmitter, which is the material of the interconnect. And not only on that interconnect, but because on silicon there will be the aluminum as interconnect. So this is embedded in SiO2. So on SiO2 there is an interconnect and the top is air. So there are the two dielectrics coming into picture. If it is in the air directly for the cables, it is only one. But in cases like PCB, the PCB phenolic resin is at the bottom. Then you have the interconnect maybe in the copper or the silver, and then air coming into picture, or some sort of what we can say the phenolic resin to protect it from the environment. So the dielectrics are changing, and in that case you have to see the combined effect of these dielectrics, also how the velocity of the signal getting transmitted from source to destination is getting affected. So now signal integrity, as we say, are the voltage level of data, that is the signal received by receiver, are exactly same as those transmitted by TX, and that basically is the issue of signal integrity. So over a signal interconnect is the modeling ideal transmission. Then first we'll see the ideal, because we cannot go to the realistic lines unless we have some modeling done for the ideal lines. Then on-chip RC and all that pair of bundles, part C of that. Okay, so reflections and terminations. So any interconnect basically can be modeled. A small segment of that interconnect can be modeled like this, where I'm considering R, L, C, and G. G is the dielectric dissipation. So is a dielectric loss as such. So these are per unit length. Then that length could be per millimeter, could be per micron, could be per mm, doesn't matter, because finally it will get, when you multiply it by the length, it will get connected. But this is basically the per unit length. And then you are considering a dx. So Rdx is the resistance of this, Ldx is the inductance, and so on. So generally R and L will determine dV by dt. The drop of voltage across the interconnect will be because of two components, whereas the current to the ground will be because of C and G. So di by dt will be determined by this capacitance and the dielectric loss factor, whereas the voltage degradation along the length of the line will be decided by R and L. So these RLC basically will cause the delays as such. We know RC time constant and RLC time constant as such. So now let us assume that this interconnect from transmitter to receiver is lossless, that is ideal, and no parasitic is coming into picture. What does it mean? That the signal which is basically transmitted by the receiver will be received. So not parasitic coming into picture, it means RC, that is no time constant as such. So immediately it is received, which is not possible, and also with the same voltage. Signal reaches the destination without attenuation. However, the capacitance always is taken into consideration, because all CMOS circuits load is always capacitive. So this will build with some rise time, with some time. And how this building to final voltage at Rx takes place, let us see. So a general picture, generally transmission line is shown by this, by means of pipe like this, where this is the source end and it is the destination. So this is the Rx and this is the receiver transmitter. However, this line is being driven by the voltage source. Now I'll come to the modes of signaling also. Voltage source is generally used, so we'll use this, but this can be IT also, or there can be differential mode of signaling also, or bipolar mode of voltage mode also. But at present, let us consider, we are familiar with this. We'll consider the single edge signaling, voltage signaling. And it has a series resistance, because always voltage source will have some series resistance, maybe 50 ohms, 100 ohms, depending upon what type of voltage source, where it is, RO coming into picture. And at the destination, at the receiver side, let me say this transmission line has been terminated by the impedance ZT. So this is the termination impedance. Now, if we consider here that depending upon at what time you are considering the voltage at any point, one at t is equal to 0, let me impress that, let me start this voltage. So that is this voltage from the VT gets impressed at the source end, and then it starts going towards the destination with some time. So voltage at t is equal to 0 and at x is equal to 0, that is at the source end, when the signal comes here, what is appraised at t is equal to 0, we'll see this transmission line as a long infinite impedance with the destination end connected to the ground. So it doesn't, basically the signal hasn't traveled. So what it sees is that this basically tries to model this transmission line as a long transmission line with Z0 as infinite, and in such case the voltage at the source will be given as a potential divider of Z0 and R0, and the voltage impressed at, that is the first incident wave voltage at the source will be Z0 upon Z0 plus R0 into Vt. So it will be less than Vt. The voltage here itself has degraded by this, and then it starts basically going towards the drain side. And at TL, generally the length here is the timing propagation delay or time of flight here is expressed in terms of TL, that is the length of the line. We always talk about Z0 and TL. So Z0 is the characteristic impedance of this, which is again material dependent, and TL is the length of the line. It means after time of flight the signal will go from the source to the destination. So at TL, then this signal will reach. And at any point, if you consider what is the signal strength at any point, at any time, is given by this Vixt, that is the first incident wave, which is coming at any point here, is what was present before a time given by t minus x by v. At time t, x by v is nothing, there is a velocity. So this is the timing. So at this time it has come, what was before this was basically present at the source, the lossless line we are considering. So what signal was present here after x by v time will go here. So when we are considering the voltage here, this will be at time t minus x by v coming into picture. So this I said, and at time at x equal to 0 and time equal to 0 is given by the potential divider. Now this is okay. So what happens is that when the this signal reaches here at the destination, it sees now it sees that that is termination impedance is of ZT. And here the reflection takes place by a reflection coefficient given by KRT is equal to ZT minus Z0 upon ZT plus Z0. So whatever signal is incident here now gets reflected by this amount. That is, for example, let me say 500 millivolts is coming here and the reflection coefficient is 0.3, then 0.15 will get reflected and again starts going here from destination end to the source end. At the source end, again you see there's a termination resistance of R0. So there will be a reflection coefficient similar to this coming into picture, which is KRS is equal to ZS minus Z0 upon ZS plus Z0. So depending upon that 0.15 has come here, a fraction of that again gets reflected here, and slowly this thing continues till the entire line comes to a constant voltage, which we would say that if the we have started this would like recognize logic 1. And at any point, this we have talked about the source and destination points, but at any point, the voltage will be superposition of what was the previous, what is the incident, and what is the reflected. So taking this into consideration, again, I'll not go into the details as such, but this you can see that how this voltage is calculated. And then I have calculated from 0 nanosecond to 112 nanosecond at source end as well as at the destination end. Only two ends are considered. When voltage at the source end and the destination end is same, we can say that the entire line has come to that voltage. And you can see by considering what was the previous, initially you can see that only the incident is there at the source end. There is no voltage at 0 there. But when you consider 4 nanoseconds, I consider time of flight as 4 nanoseconds, the incident is what was coming from the source is 0.11. Depending upon the reflection coefficient, it is 0.100. So total is 0.211 voltage at the destination end at 4 nanoseconds. Now this reflected 0.100 is incident on the source at 8 nanoseconds because 4 nanoseconds is the time of flight. The previous was 0.11, incident is 0.100. Depending upon the reflection coefficient at the source, this much gets reflected. So at the source, this is the addition of all these is the 0.289 and so on. So this way, this simulation, I mean, this working has been done up to 112 volts, because you see now the voltage at the source end is 0.704, 0.704, or you can say after 64 or after almost 80 nanosecond is almost the same. There's only 3 micro, how much it is, 3 millivolts difference only is there, 3 millivolt difference is there. So for all practical purposes, this can be definitely considered as logic 1. So you do not have to really wait for 100 nanoseconds, but definitely you have to wait at least for 64 nanoseconds till the voltage at the source end and the destination end comes to the. This basically is a graphical representation of this. So at 4 nanoseconds, the voltage at the destination has some value depending upon how much is impressed and how much is been reflected and so on. So this is at the source end, the voltage slowly builds up, whereas the destination end, that also builds up. But at any given point of time, you can see that the destination voltage will be higher than the source voltage. And then you see that almost after 64 nanoseconds, that is 8 round trips, 4 and 4 is 8 nanoseconds. So after 8 round trips only, the voltage at, we can consider, yes, receiver has at least received the logic 1 and the complete line has come to a stable voltage, and now you can impress the other symbol. So only 64 nanoseconds or 80 nanoseconds to be very sure of it, we can send the second symbol, and this is the thing which is coming into picture, a lossless line. This we have considered a lossless line. Now we cannot now depending upon the termination, what is the how do we terminate it? So the termination can be here with the match termination, that is, it is Z0. That is what is the characteristic impedance of the transmission line, and the termination also is Z0. In that case, you will see that the transmission coefficient comes out to be 1. What does it mean? When the signal reaches here at the termination after a time of flight, it gets double, because incident is this, and then it gets reflected by the same amount. So the voltage level, that will be doubled. When you consider a termination with open circuit, there's no termination here, which basically is the case of our CMOS circuit and very, very beneficial here. Yes. Here, did I say the voltage doubles here? The voltage doesn't double here. Is the voltage here, which basically is previously no voltage was there, and reflected voltage only will be there, and hence the same voltage level reach here after 4 nanoseconds. Now here, when we consider open circuit, it is ZT minus Z0. ZT is 0, so KRT will be 0. 0 KRT, it means there is no I'm sorry, I think we are considered to the match termination here. Here, basically in the match termination, what is incident is being absorbed in the termination register. It means is given to the receiver. So receiver receives exactly the same after a time corresponding to the time of flight of with KRT is equal to 0. So this is, I always we say where the match impedance is there or not. When match impedance is there, there is no reflection. Everything is absorbed in the termination resistor, and that is what we want, that receiver should receive. So this is a good thing. But in the CMOS, we know that capacitors are the input impedances, so that basically is the termination. So it is an open circuit. So KRT is 0. With KRT is 0, it means there is no reflection. Am I making some mistake? Here the voltage gets double. The incident voltage is here, and the reflected voltage is, I'll come to this point, but you can keep in mind that the reflected voltage here, that is the voltage at the destination, gets double. And when the termination is ground, connected is a short circuit, then KRT is -1, and hence you will have the incident signal and the reflected signal basically cancelling each other, and there will be no voltage on this one. So depending upon that, either you can go for the match termination, or in the CMOS case, we have this where the voltage at the destination will double. So even if it has got degraded, like I say 0.7 will become 1.4, and now the devices there will again bring it to the true logic levels to reach the proper logic levels. So this is what the effect of the termination is. Okay. So practical HSD system, as we are saying, that TLC is a capacity load at the termination with high impedance as if it is open termination. The incident signal after TD gets fully reflected at the termination, and full reflection takes place. That is why incident plus reflected gives you double this one, which basically, however, this again can go back. There will be multiple reflections, as we have said, and hence practice is to put. Now what happens is that in the CMOS circuits, at the termination you have open, but at the receiver you have some supply resistance as such, or the impedance as such, and hence even if it gets double and the reflected signal is as strong as the received one, when it comes to the source, it will again get reflected by KRS, that is the reflection coefficient at the source. So if you put a series source resistance of value Z0, again KRS also will become equal to 0, and it will be absorbed in that. There will not be multiple what I can say reflections here. So this approach will be used in high-speed circuits where open termination at the destination at the receiver side and match impedance at the source side. So this basically is something where at the source side you have the match impedance, which is same as that of the characteristic impedance of the transmission line. So this will be, as from the waveforms you can see, that this will come to a stable state, the entire thing, after a period corresponding to the round trip, which is the 2dd or 2 time of flight. So after 2dd, then you can send the next symbol. So this basically the practice followed here. Now this was the lossless lines. Let us consider now both RLC and RCSH. So as we have said, this will cause the delays. So let us now model the RC transmission lines which are on chip and then RLC. So when you consider that for short lines, L is 0. Actually, except at the package pins on the silicon, generally the L will not come into picture. And the dielectric use will be such that the dielectric loss is almost 0. So we can ignore the quantities corresponding to the degradation taking place corresponding to L for V and for I as far as G is concerned. And then the governing equation over a transmission line, which is basically called as the diffusion equation, the second order space differentiation is given in terms of the first order time derivative of the voltage. So this is basically the diffusion equation. It means signal diffuses with RC time constant on the line. So if you can see this, I consider a 10 millimeter a transmission line. The signal at x is equal to 0, at t is equal to 0 with rise time is like this. But then you can see at various distances from the source, they go on increasing. It is having a sort of diffusive nature with final value coming only after some, depending upon RC time constant. And even for 10 millimeter, you can see that even for this time, whatever simulation has been done, the final value hasn't come at all. So you will have to wait till the complete line gets the same potential. It means the receiver is receiving the same logic level as was given there, as was said by the transmitter. So this delay is basically proportional to the length. I think D is the distance, or we can say length square, length of the interconnect, or at a D, because we can consider any point X. So we have said it is a D square, a distance from the source end. Is given by RC into D square. Again, RCR per unit millimeter of the length. Rise time is proportional to 0.4 D square, is 0.4 into RC. So it is 0.4 times of this delay. So let us consider that we want a bandwidth of 1 gigahertz. So bandwidth is, we know that 1 upon 2 pi RC. So RC will come out to be 16 nanoseconds. Delay is if we want delay of 1 nanosecond, because 1 gigahertz, one cycle time will be 1 nanoseconds, we'll limit the length to 1 by 16 under root of that to 0.25 mm. And then the rise time will be 1 nanosecond, 40% of this will be 400 picoseconds. We wanted in a cycle time of how much it is? 1 nanosecond. So delay of 1 nanosecond and rise time of 400 picoseconds. However, now if you consider TR equation 0.35 upon bandwidth as such, this is the rise time, and considering bandwidth specification, this comes out to be 3 nanoseconds. On the other hand, here it is giving as 400 picoseconds. So here the discrepancy is there in this. So either we have to reduce the we have to reduce the bandwidth, or we have to use the multipole filters multi-stage filters, so that these specifications will be made. So, I mean, as I stressed in the part A of this, bandwidth and TR, you have to keep an eye, and a trade-off will always be there between the two. Let us lossless LC lines. Here we have L and C coming into picture. Again, R and G are omitted. So the equation which will be governing here is d2V by dx square, second derivative of the voltage with respect to space. Is spatial basically is second order time derivative of the voltage as such. So this is a wave propagation equation. And very important thing here one should keep in mind is that this wave, when it arrives at any point on this transmission line, will set up a forward and a reverse traveling wave on the transmission line. So this basically is something which one will have to understand, that because of this, there will be now, the two waves being set in the forward and as well as in the reverse direction. Z0 is given by, that is the characteristic impedance of this transmission line is given by under root L by, very much dependent upon L and C, whereas the velocity in this is given by 1 upon root LC, and hence that time, that period will be root LC. So if you want that period should be reduced, L and C should be reduced. So, again, you have to have some sort of trade-off or some design parameter which will have the required characteristic impedance with required velocity, so that TR is, propagation delay and speed is obtained. Again, another drawback with LC circuits is that this acts as a tank circuit, and in the absence of match ZT, if there is no match termination impedance, then it will set the oscillations, and these oscillations again are not good for the digital lines, and we'll have to see how we can suppress those. In case of LRC, now you have RC component coming into picture as well as LC. LC will set the propagation wave in the forward and reverse, whereas RC is the diffusive. So it is a combination of diffusive component and the wave propagation. So the governing equation here will be d2V by dx square is equal to RC, diffusive part, and this is the wave propagation part. Now, if you consider that 500 micron and 1000 micron, how this will be, as far as this is concerned, it is a fast rise will be because of the LC or LRC, whereas the slow tail will be because of the diffusion. So these dotted lines basically are at 500 microns and 1000 microns because of the diffusive part, a long tail, whereas the fast rise is because of the LC at the different points. And then totally it will be a sort of combination of these two. So as far as signaling over LRC is concerned, yeah, I think we'll come to that. Now, R also is there. So we have to consider the LRC as such. And then there will be a tank circuit coming into picture. So design tip will be, we like to dampen the oscillations. Luckily, in this one, we have a very high impedance here. So the match impedance is not there. There is ZT large, and hence we have the signal getting double, but we do not want the oscillation. So again, you can put some in higher resistance here, and we'll have to attenuate. That is, the amplitude gets attenuated again by increasing TR, because this amplitude attenuation is given by the equation 1 upon omega naught, that is F naught upon TR. F naught is given by this 1 upon root LC. So everything, again, whatever you get the oscillation, the frequency is depending on L and C components, as well as the attenuation in the amplitude is dependent upon TR. So the decrease in the, that is KR can be reduced by increasing TR. So again, TR coming into picture. Now this basically is some sort of simulations, again obtained from some standard book. You can see that the R value is being, because we said that oscillations will be damped if R is increased. The Q quality factor is also 0, 5. This also is going from infinity, sorry, this is infinity, 5 to 5. The quality factor is decreasing, whereas R is increasing. And now you can see that here there's a sustained oscillations which we want in the oscillators, but we do not want in DC circuit. They should be damped. So as the resistance is going on increasing and the quality factor is going on decreasing, you can see the oscillations are getting damped, and higher a value of resistance you have, maybe after one cycle it stabilizes. So value of R is very important. This basically for F naught is equal to 500 megahertz. So 2 nanoseconds basically is the period of this, and Z naught is 32 ohms. That is square root of L by C. Now, considering the second figure here, that is, we say that let us consider this and let us study further what is the effect of TR. So here in this, we have taken this second waveform where TR is 0 here, R is 4 and Q equal to 2.5. R equal, and this we have taken. R is equal to 4 and Q is equal to 2.5, where TR here was not taken into consideration, but when we take TR into consideration and have the change from 0 to 3 nanoseconds here, you can see that again the oscillations are less, that is, it will get basically stabilized at a lower time, and hence a proper choice of LRC is required to damp the oscillations, which also is a culprit to create the noise in the digital systems. So rise time and round trip delay limit the maximum data rate. We can decrease the length of TL, but maybe or may not be in hands. Another thing here, I think, which perhaps I think in microelectronics, when you consider putting an inverter in between will decrease the delay. So if there is a long line which is having, there's a long line and that is hampering your work as far as speed is concerned, you can divide it into number of parts and put an inverter, the total delay will be less. And that also is another, at the device level, one can do that solution. Increase the time constant of the transmission line proper and all that, and velocity basically is 1 by root LC, increases and can work with high speed. If at all you change the dielectric medium, in the dielectric medium Desmi decides the velocity at which your signal will propagate, and hence a proper choice of the dielectric material also can lead you for your design at higher speeds. Now, intersymbol interference is another thing, that is, as I have said, that ideally we consider transmission line is a memoryless, doesn't have any memory of the previous bits. But in reality, there will be reflections, as we have said, from the termination, from the source, if matched terminations are not there. Then there will be magnitude and phase of the excited resonances coming into picture. And the signals, as we have said, maybe by the end of the cycle do not reach the power rails, because finally the power has to reach the power rails, and this will affect the transmission of the current bit. Now these ISI, there are three reasons we have said: the impedance mismatch, resonant circuits, and not reaching to the final. So let us consider ISI due to impedance mismatch. So this is the transmission line with characteristic impedance Z0 and the length of the line as TL, and is driven by here we are driving it by the current source. Why we'll come to know in a minute. And it is a termination, RT is there, but it is not equal to Z0. It's a match termination is not there, it's a mismatch. So ZS, now here we can see ZS is large because always the current source will be with a high resistance or impedance in parallel. So this has been terminated here with large open termination. It means at the termination, you do not have the match, there's a mismatch. But here, what you have done, you have kept it as a large. So current source driving unit amplitude pulse with TW, that is pulse with TW, that current basically is driving this with a current pulse of with TW. After TR, it will reach here and get reflected with reflection coefficient. We know RT minus Z0 upon RT plus Z0. The reflected with amplitude, now the reflected view has an amplitude. Let us consider that it has been driven by 1. Let us say that this has been driven by 1 volt amplitude and the pulse width of TW. So after a TL length, it gets reflected from the termination with reflection coefficient KR. So 1 into KR is KR. So KR voltage is coming back. Now after 2 TL, it will arrive at the source, current source, where it is an open termination, so it will get doubled. It means it becomes KR and KR. So again, KR will get reflected. Now this KR after 3 times TL, that is 1 round trip and again from source to destination, goes to there and get reflected KR by KR. So KR coming, KR reflecting, so KR into KR will be KR square. So like that, if you go on doing multiple reflections between source and drain, you will find that after n such that amplitude at the source end will be 2n times TL, that is Kr raised to n. So if you can see here, after 2L it is Kr, after 4TL it is Kr square, and goes on decreasing as the you consider that number of round trips. However, this, at least for the first, depending upon Kr or even second, will come into picture, and this we have considered only at the source end, at the destination end. Now what happens is that when the wave is moving, now this is the current pulse at t equal to 0. This will move maybe some 10% of x at some time. So there also that will again, that reflections in, I mean that reaching at the destination will give the reflection. So as it is moving from source to destination, every time such type of reflections will take place, and there is a chain or the epochs, you can say, of such reflections which take place, and then it gets the superposition of entire echo train, giving you the total mismatch coefficient as Kr upon 1 minus Kr. So the reflection coefficient, that Zt minus Z0 upon Zt plus Z0 coming into picture here. And if this is, I think there is slight, if you consider that there is a slight mismatch, now you consider slight mismatch is there. You try to match it. You wanted Z0 equal to 50 ohms, but RT was 45 ohms, and there is a mismatch of 5%. So if you consider that Kr, then Zt minus Z0, that is Z0 into 1 plus epsilon and all that, it will be approximately epsilon by 2. That is, for small values of mismatch also, the reflection coefficient is half the mismatch. And then if Kr is very small, only the first reflection is the receiver. And you can, the solution for this is that receiver can be designed knowing the history and the round trip time to subtract the reflection crosstalk voltage from the received signal. That is, you do the experiments in the initial stage and try to see after how many reflection and what is that which is coming into picture. So at the receiver end, try to have some hardware where from the received, this reflection crosstalk will be eliminated, and then even if mismatch is there, the received signal will be okay. So you have to have some sort of simulations, or we'll have to see actually what is happening and correspondingly give some solutions that the received signal is okay. This could be because of the resonant circuits, as well as LC tank circuits, and the next bit is sent even before the first has stabilized and will corrupt the next bits, and putting a damping resistance in across, I mean at the termination, will damp these oscillations we already have seen. There'll be sort of inertial. We also, I mean, all those who have done these CMOS relays and have worked with Xilinx FPGA tool as such, we know about what are the different type of delays. The inertial delays which are associated with the component, whereas the transport delays which are associated with the interconnect. So inertial delay, if the propagation delay of the component is large, then again there is going to be, if we try to impress the next symbol again at the input of this, then the retention of the previous, it hasn't stabilized, but some part of the previous getting superimposed by the other will cause some sort of the what you can say the run pulses, or you can say some going high, going down, because the things are happening very fast. And at the intermediate you will have this, but this again will be inverted by C, and you will get some sort of things which are not going, sometimes not going to the logic levels properly, and again returning back because to the low voltage. So it's something which is a phenomena which is taking place between the logic levels. If you try to catch the eye diagram of this, to this I'll come a bit later on, what is eye diagram and how it is useful for consideration of the amplitude attenuation and also the timing attenuation. But at present, if you try to catch this eye diagram, here you will see that the total attenuation of the amplitude has taken place and could be an unpredictable result here. So the simple solution here is that just put a feedback from that C to the B, and then what you can see, the eye diagram and the received signal is going to the proper logic level. So such type of solutions can be done to have what you can say interference of the previous signals because of the inertial delay. So practical high-speed digital systems have CMOS devices. So transmission lines is capacity load at the termination. I said always, so it is open termination. The incident signal after TD gets fully reflected at the termination. The signal at the destination doubles. So after 2 DD, fully reflected signal arrives at the source. What is reflected at the source? So you put a match termination at Z0, so it will get absorbed completely, reducing intersymbol interference and crosstalk also. So for off chips, that is LRC, oscillations will damp by using a proper resistance, because now here CMOS circuit approach is common in high-speed circuits. So CMOS, I mean, we are comfortable because the input impedance of CMOS is very high and the termination scene will be high, and this will basically not cause that problem as any other bipolar circuit as such, where there will be some sort of input resistance or the termination which will not be matched, or the open as such, giving a problem for the crosstalk. Any doubts so far? Because I have completed the signal integrity over 1, where we have seen that there is, because of these components RLC, how the signal is getting corrupted and the signal doesn't come to its final value within a time corresponding to the time of flight or the time required by the high-speed design, depending upon the bandwidth or depending upon the maximum frequency you want to work. Now let us, we can move on to the bundle of interconnects, a pair of wires, and how this capacitive, inductive, and noise comes into picture, we'll see. So any doubts so far you can ask.
Ma'am, shall we
Break.
take a small
Shall we
break?
take break?
We should take a break, or what? What is your suggestion?
I think participants, if they want break, we can have it. A 10 minutes break. Now it is 11:15, so almost 1 hour lecture. If they are bored, and then we can continue at 11:30. And I think yeah. Sir, if they are not tired, you just ask them. You can take the poll,
okay.
or you decide.
No, but no, I'm because this is part C, means you will take up to how much time you will require to complete everything.
Part C will be 30 minutes. Part C 30 to 40 minutes, and that will be again 40 minutes. That is synchronizers. So 40 plus 40, 80. That will be 1.5 hours.
Acha.
So 11:30 also, even if we take, I think by 1, I think we can.
Acha, then you continue, madam, for some time. No? Then that is okay.
Okay. So I continue.
Okay, ma'am.
No, should I continue or wait?
Yeah, because nobody commented, so I believe we should. One comment has come, I think.
Nobody commented.
Comment is go slow. That is again the comment is go a bit slow.
Okay. What I want to say is that whether the participants are there or not.
Yeah, they are there.
Otherwise, I mean, in a class, we come to know that the students are not there.
Yes.
Here, we do not come to know, and hence a blackboard and the teacher, and maybe like this a joke. Concert होती एक म्युझिकल कन्सर्ट, आणि हळूहळू सगळेजण उठून गेले. एकच मनुष्य बसला होता. जेव्हा त्या गायकांनी डोळे उघडले तेव्हा दिसला की एक तरी माझा ऐकत बसलेला आहे. अरे वा, यू आर इंटरेस्टेड. तो म्हटला, नाही, तुम्ही ज्या सतरंजीवर बसलाय ती माझी, ती नेण्यासाठी मी थांबलेलो आहे. तसं मलाही असं वाटेल की ॲट 1 o'clock.
So as if I am there too.
So I am just going on speaking.
Satranji Gurdalala.
And only Rathod and Priya Deshpande and the Priya will be there, I think.
Laila madam ऐकतायत लोक.
कारण ऍक्च्युली आपलं म्हणजे ऍडमिशन्स आणि रजिस्ट्रेशन फुल झालं होतं खरं पहिल्या दिवशी, जेव्हा लास्ट डेट होतं त्या मला खरं तर मला
Actually, no. What people do is people register because it's a free. No, that's the drawback of having the something free. Because you register, we got so many registrations. In fact, the data science course, when I opened the link, madam, within 2 hours we were having 60 to 70 registrations. Within 2 hours. So next day we actually almost we sort of closed. This is like that. And here also we initially we got the registrations, but it was a little bit slow. But we had so many registrations, and finally people, because it's free, no, we are not charging anything.
फ्रॉम द फर्स्ट डे अँड दॅट इज व्हॉट आय बेसिकली फील सॉरी. कारण काय काय तर तुम्ही पण दिली सर आपण ह्याच्यामध्ये SPI नॉर्थला वगैरे दिली किंवा मी पण नंतर दिली. तर तिथं
बरोबर आहे.
रिस्पॉन्स इतका प्रचंड मिळतो त्या नॉर्थच्या कॉलेजेसपासून की खरोखर पार्टिसिपंट्स इव्हन टिल द एंड टू मेनी पार्टिसिपंट नॉट फॉर द आय मीन सर्टिफिकेट किंवा रजिस्ट्रेशन
Correct,
पर्पज
correct,
दे
correct,
इव्हन
correct.
इंटरॅक्ट. So तो महाराष्ट्रामध्ये somehow I feel very bad की why it is less. Only we are conducting these conferences and
Correct,
असं म्हणजे
correct.
थोडंसं वाटतंय की why we are so inert as far as such things are concerned, which definitely
So
I mean
that's why we have taken, madam, you will not believe, yesterday evening we had a meeting, including
हा
principal sir. We had a detailed discussion, and we
हा
are reopening all registrations now for all courses.
हा हा हा
Because I believe now we came to conclusion that as if we have to have 200 registrations, then probably 70 people will
yes
turn
will
up.
be there yes yes yes.
So we are reopening all registrations. We are reopening, and our system admin is working now. With 15
हा
minutes,
हा
we are going to reopen all registrations. What do we do now?
हा हा
Then,
हा हा
because so resource funding is there, resource person
हा
like you, there are so many resource person available. They are giving their
हा.
time, and then
No,
people are not coming up.
I think participants only see the affiliation and then try to attend and they don't feel interesting. They leave the meeting and all that
Right,
because
right,
I see
right.
only Abhishek Kumar is here, nobody else other than. Is this so?
No, 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 madam. That you can't see there. There are 28 now.
ठीक आहे
You
ठीक आहे ठीक आहे.
हा तुमच्याकडे ते विंडो छोटी येते ना तुम्ही प्रेझेंट करतात म्हणून.
हा
That's
हा
what
हा.
you can't see. People are
Actually,
there.
I request participants to give some sort of ask some questions. Let it be interactive. Let it not be katha kathan. Vapu Kale. I am
Manisha
Shaila
madam,
Subbaraman.
Manisha
I
madam,
am.
are you understanding the topic?
This is
Okay.
what as a student make us.
Okay, madam. You
Any,
continue for 15 minutes.
okay, I think we'll wait for 15 minutes, 10 minutes. We'll 11:30 we'll start.
Okay, we'll start 11:30, ma'am. We'll
Okay,
start with
okay,
11:30. Okay, okay,
okay,
ma'am.
okay.
Okay, break.
Surprising.
जिओचा काहीतरी प्रॉब्लेम आला. जिओचा प्रॉब्लेम तुमचं हे आहे नीरज आहे.
नीरजला कॉन्टॅक्ट होत नाही का?
बाबा आज तू काय सांगते, नीरजचा आता चालू आहे सेल्युलर म्हणजे जिओचा काहीतरी प्रॉब्लेम आहे.
नीरजला कॉन्टॅक्ट होत नाहीये का?
नीरजला बोललो ऑलरेडी.
ओके.
त्याच्या काल 10,000 झालं.
इकडे आल्यात तसं दररोज 10,000 मिळाले ना 1-2 महिने तरी चालेल. 1-2 महिने दररोज 10,000 मिळाले ना ऑन एन ॲव्हरेज तरी चालेल. त्याचं सगळं मी पे बी त्याला खर्चासाठी राहतात. माझं
मला टॉफी कुठे आहे?
नको म्हणला तुम्ही. हॅलो हॅलो.
हा मॅडम.
हा चालू करायचं.
हा करा चालू.
Okay, okay. We come to the part C of this presentation, where we are going to consider the signal integrity over a pair, two wires, or a bundle of interconnects. So we have seen capacitive, inductive effect. And then how we'll say that how the other line, that is we have said about the aggressive and victim also. One where the transition is taking place is the aggressive interconnect, whereas the nearby is a victim. So how capacitively any transition or inductively gets coupled with the other line which is not supposed to make transition, and that basically cause a noise as such. There are so many lines. Generally, the return ground is one, and all the signal lines from this destination come to one common ground. So there is, though we consider it, it's maybe it is the ground is common from the receiver to the transmitter also, and hence it will have some interconnect again. And depending upon at what point or node we are looking, there will be a variation in the resistance or the impedance being offered to the signal at various points in the node. And hence, depending upon when the transition takes place, there's a current loop, and the current drawn flows through a return line, and across this impedance gives a voltage, which again is a noise voltage, adds to the crosstalk. So what is the return signal crosstalk, and how we can tolerate, or how many lines should share one common ground? We have seen many microprocessors have 2 or 3 ground pins. Why? That is to basically, I mean, one of the reasons for that is to limit the return signal crosstalk. And then we'll come to the noise, where there will be a proportional noise, which noise is proportional to the signal swing. Independent noise like receiver offset, receiver sensitivity, other power supply not related with this circuit, making transitions, changing the voltage levels, and the statistical noise. So these will add, and we'll try to see what is the noise budgeting as such, and then come to the solutions. So considering now, signal basically is electrical nature. It could be a voltage signal or current signal, as we know. Signal gets coupled with adjacent wire through coupling capacitor, which is the mutual capacitance or mutual inductance. This coupling causes a crosstalk which affects the quality of signal flowing through the wires. So this is a circuit A, circuit B. Circuit A may be driven, let us say, or there is a basically the current flowing through this. This is because of the electric and magnetic fields. Magnetic field in case of the inductance, and electric field because of the in the capacitance. So there is a mutual, beside each and every circuit will have its own capacitance with respect to ground, but between these two circuits there is a mutual capacitance, and the AC current flows through that, and the transition taking place on this, the voltage level going from 0 to 1, because of this capacitive coupling causes some noise in this, that is capacitive coupling. As far as inductance is concerned, let me say that this is some driver driving the transmission line having some inductance. This is another nearby, and the current through this causes a back EMF here, which basically induces a current into this and causes a voltage, which again tries to oppose the current. So this basically, this inductance, it will have, the parts will be series inductance and mutual inductance. This also will have a self inductance, which is series, and the other one is a mutual inductance. So these two lines are mutually, they are inductively coupled through mutual inductance as such. So these are the parasitic parameters, that is coupling capacitance between the two, or the mutual inductance between the two lines, are basically high parameters which affect the high performance. Will not be that effective at low frequencies, but affect the high frequency performance. Let us consider capacitive coupling first. Because the A and B lines capacitively coupled. Let me say the transition takes place on line A. The voltage level goes from 0 to 1. Now, by the coupling coefficient between this is the CC is the coupling coefficient, coupling capacitor, and B is having a capacitance with respect to ground, let me say as C0. Then, similar to potential divider, the voltage voltage developed on this because of the transition on this is given by coupling coefficient, which is Cc upon Cc plus C0. And hence, the moment transition takes place, there will be a sort of voltage spike which slowly degrades and comes to 0. But this is a sort of noise which is created when the line A is making a transition, and this propagates along the transmission line towards the destination and will be received by the receiver also. Now, in the capacitive coupling, what happens is that such type of transition taking place on A sends a positive diffusive signal in the forward as well as in the reverse. So both are the positive, you can see. A similar thing happening in case of the inductance. Now, always, again, A is having some transition and the crosstalk voltage is developed on B because of the mutual inductance coming into picture here. But always it is in the direction opposite to that. So in the previous case, it was in the direction of the transition, whereas in case of the inductive coupling, this B will develop a noise voltage which is in a direction opposite that depending upon what LM is. So there is a mutual, that is this inductive coupling coefficient is given by L by M as such, which is the mutual kind. Another important thing here is that when this is making a transition, A is making a transition, in the B, whatever noise is developed here because of this coupling will send a negative wave in the forward and a positive wave in the reverse direction. So what you see is that for the capacitor, both were positive. However, for the inductive coupling, one is the negative at the far end and the other one is a positive towards the near end. Coupling, that is, if you consider the combined effect of the capacitance, capacitive coupling and the inductive coupling, you can say if this coupling coefficient, capacitive coupling coefficient and the inductive coupling coefficient are a match, then at the far end, these noise will get cancelled and far end will not be of much concern from receiving this noise. But at the near end, both waves are positive, this will be high. So when we consider RLC line, what is the noise which is created because of the capacitive and inductive coupling becomes a point of concern. So I think this KCX is given by CD by C, the coupling coefficient, and C is CD plus CC, whereas the inductive coefficient, coupling coefficient is given by M, that is the mutual inductance divided by the self-inductance. Generally, we assume that both the transmission lines are identical as far as length, material are concerned, so they have the same parameters. So I have said about this, that at the near end gating, that is the forward traveling wave, will have a coupling coefficient given by KCX minus KLX, because one is positive, the other one is negative, and hence the average is by 2. But if KCX and KLX are matched, then forward crosstalk coefficient will be almost 0 and far end will not receive any crosstalk voltage. However, at the receiving end, we have the total coupling coefficient given as KCX plus KLX by 4. So reverse coupling coefficient and forward coefficient also needs to be taken into consideration if the couplings are not matched. So let us consider this is the transmission line and we are extending again. These two lines are traveling in parallel, and hence any transition taking place, let us say on A, definitely will cause some sort of crosstalk voltage on C. Now here also we see that A has been driven by the voltage source, whereas C is supposed to be at whatever potential it was having before A makes a transition like this. But when A is making a transition, let me say at some time, and then it is traveling towards destination, that is towards the point B, after a time corresponding to the length of this. So it is received here. Now, this traveling here basically is going to set the inductive and coupling, considering both in the forward direction and in the reverse direction, the waves as such. Considering only these points, now the wave which has gone to B causes disturbance here, which is seen here. But when you are trying to consider it, how it travels, this is going to travel towards C. So this is disturbance or the noise voltage caused at point D because of the transition here, coupling from B point to the corresponding D point, but it is negative. So it, if they are matched, is having almost the same value. And for a small time, there is a sort of glitch here or a run pulse, you can say. But then this reverse traveling wave, after again a round trip time, after again a point TL, comes and whatever was voltage here is a negative, comes to a steady state voltage. That is at C, you can see because of this RLC, you have the noise voltage being created for a time corresponding to the round trip time. Far end is not that important. It's a very small and maybe absurd. We have to take what is the level as such. But at the near end, you see that this crosstalk voltage or the noise voltage persists for a longer time. So of course, we cannot send the next data till the entire transmission line attains this equilibrium. It means we have to wait for the round trip time, and this will obviously limit the sample rate. So how we can speed up? The culprits are KCX, KLX due to mutual inductances CM and M. So we can take some action. Again, I will not go through this, that how we can provide the ground planes to guarantee that quick return path for the high speed signals. That is, even if some noise is there, it immediately gets grounded. Ample space and the design rules between pair of high speed signals. Any technology will give this sort of design rules. And when you are using 90 nanometer or 35 nanometer technology, the library files will give you these guidelines, and they will not get, anything which is below the specified limit. You can use higher than that, but not below that. And hence, these are some of the things. Provide decoupling capacitors, because decoupling capacitors, which is provided to the power lines very near to the pins, will try to any glitch or any sub noise coming, will immediately take it to the ground. So use as many ample of decoupling capacitors. Then connector pins, ensure to have clear ground cutouts around the pins to provide a return path. We see return crosstalk is there. So provide the number of pins, and provide separate region on the board to house all sensitive analog circuits away from high-speed circuits. In the previous talk, I was talking about the eye diagram. This basically is a means of determining the signal integrity. Now, in all the cases, whatever crosstalk and other one we have considered, the signal is getting attenuated. Now, if at all a signal, you can concentrate on this figure. If at all the signal is making a transition from 1 to 0, we will always see that it doesn't go to true logic 0. It will be at some level which is very near to the ground level. Similarly, when a signal is making a transition from 0 to 1, it will not go to the supply rail voltage VDD, but to a voltage slightly less than that. And hence, if we consider this, over this, there is a time that is spent because of the delays. And also this amplitude, now if you see between logic 1 and logic 0, the this voltage, the difference between the two is definitely less than what it should be if the true logic level it would have achieved. And then this window is basically this eye opening. This window is eye opening. In the, if you try to superimpose at a particular place on your circuit, the number of waves like this, where making a transition 0 to 1, 1 to 0 rapidly, and then you catch it, you will see that your thing is going something like this, where there is an eye opening for an amplitude corresponding to 2a minus 1, where a is 0 to 1, how much that is, and similarly we consider 1 to 0. So this opening basically will be, if you calculate, will be 2a minus 1. So this will be corresponding to 2a minus 1, where a is the, this transition voltage is from ground to, let me say, if it is 1.8 is going to 1.6, so a is 1.6. So 3.6 minus 1 is this what you are getting here. Now, also you can see, because of the rise and fall time, even timing wise, we do not get the full cycle for basically receiving the signal. The timing also has been reduced. And if at all the receiver has to receive the data, which is without corruption, then it will be the responsibility of the designer to align the receiver clock at the center of this eye. This is an ideal. What will happen is that, suppose if A is 50%, that is the signal from logic 1 to 0 reaches only 50%, 1.8 goes to 9, and from 0 goes to up to 0.9. It means A is 50% of this. Then 2a minus 1 becomes 0, and there is no eye opening at all. This is the worst case. There is no eye opening. It means there is no region in this eye where you can align the clock of the receiver to detect the symbol. And hence, there is a timing wise as well as amplitude wise attenuations. And hence, it is very, very necessary that you check the digital designs for these eye diagrams, giving sufficient, timing for you to probe, and also the amplitude, which can give you the correct logic levels. So this is basically something which is very, very important in this one. Now let us consider the signal return crosstalk. So what does the basic circuit theory teach us? That logic signals are propagated by the flow of current, and these currents always flow in loops. We generally, as we have said, try to see on a digital circuit only the voltage. We talk in terms of the logic level, that is the voltage levels. Logic 1 is this voltage, logic 0 is this voltage. We never talk, I mean, the specifications are given in the data sheet, but we do not consider IH and IL or IH mean and IL max as something like that, the specifications. Even if you consider the schematic of any digital circuit, nowhere power and ground rail has been shown. Is assumed, is not shown. And hence, we really do not take into consideration these, whether, the ground very seriously. But we know from the basic theory, when a current flows is because of the flow of the electrons, and all the current finally has to return to the loop. It cannot happen that electrons will stack up, that is, you are transmitting it from transmitter to the receiver, and there is you are driving it by the current source. Do these electrons from the current source go to the receiver and stack up in a bucket like that? It will never happen. So electric field generated by each, if it happens, the electric field will be generated by these electrons piling up, will repel the further electrons, and the current will not flow. So it will never happen. It has to follow a loop which finally goes to a ground, and hence current will always be in the loop and going back to the ground. And hence there is, all the signals might have been driven by the different drivers, but the return part of all the signals is going to be same. And hence there is a current, I mean, if many signals are getting switch at a time, there will be a large return current from all adding up, flowing through the return path, and depending upon the resistance, you will have the return crosstalk coming into picture. So though it is not shown on the schematic, we should always keep in mind that current also is important, and we should see that we have, and that is why we say give proper, ground at the various places very near to the pins. So all signals in reality share common return path. A spurious noise or the crosstalk which is generated on one line will affect the other lines through return path. That is, the voltage which is created because of the current, return current flowing through this impedance will create a voltage which again through the ground pin will get superimposed on the other, which basically cause this. It means complete corruption of the all the voltages on the various signals will take place, and hence we'll have to compute the noise voltage, how much noise voltage is getting created, and whether it is within the noise margin. And if it is not, then how can we decide that how many signals will share a ground pin to absorb this noise, and design for number of ground pins as well as the rise time of the signal. So this basically is again one design aspect. Let us consider a case that there are three A, B, C as the transmission line being driven by the voltage source VA, VB, VC. All generally will have the return path, and this return impedance is given by LR. Generally, it will be a pin or the resist. It could be impedance as such. Will not say only inductance, but generally the current is flowing, and any change in the current will cause an impedance. The voltage across this. So it has been modeled as an return impedance. So though all are driving the signal separately, the return path is common. And let us consider a case where all but one are switching simultaneously. Suppose there are 10 signals which are sharing like this, then one doesn't change. It remains either at 0 logic level or 1, but all other change, which can happen many times, like when you are going from 0, 0, 0 in 4-bit to 1, 1, 1, then all the 4 are switching simultaneously. So if all but one switch simultaneously, the noise voltage generated because of these currents flowing through this gets impressed again on all those which are the victim as well as the others which were the aggressor also, and this voltage will be n-1 because one is not switching, n-1 into LR into what that rate of change in the current is. So this can be greater than the gross noise margin, and hence design that whether n, what that n should be, which will share a common return path. So for example, if L is 10 nanohenries, let us say, and noise has to be less than 100 millivolts, di by dt is 2 ampere per microsecond, then as per this, n has to be less than 5. So this is basically a guiding equation for determining how many signals will share one return path. And also di by dt, important parameter to consider. Hence, you are considering like this, the total reflection coefficient is given by, again, this you can see in the theory, we will not go into the details, is n minus 1 into ZRT. ZRT is this termination resistance divided by R naught is the supply source resistance, and Z naught is characteristic impedance is given by this. What does this indicate? This indicates that this coefficient will be low if R naught is high. Z naught perhaps is a characteristic impedance depends on L and C. We may not be able to take part. I mean, we'll not be able to control that. What we can control is R naught, that is the resistance, series resistance of this. And here the current signaling takes an advantage. If instead of voltage signaling, if we use the current signaling where this R naught is going to be in parallel with this and being very high, this coefficient will reduce. So if at all we have to reduce the return crosstalk coefficient and the return crosstalk noise voltage, then current mode signaling is preferred one. So coming to the signal mode, very signal mode. So we have already seen that we are using voltage signaling. Driving the devices as well as transmission lane with voltage mode signaling is a common thing. But when you consider all these things, we have to consider that perhaps the current mode signaling will be better, and especially from this crosstalk return signal crosstalk point of view. Another signaling mode is differential signaling. In the differential signaling, what is done is that there are the pairs of transmission lines. If you want to send one, and these are driven by the two voltage sources. At the receiver side, you are comparing the voltage across these resistors, terminating resistors. This is a common ground. As such, you can see this is the common ground. So the voltage here is seen with respect to ground as well as here. Now, when you want to send symbol 1, or when we want to make a transition, that it goes to logic 1, then 1 is sent on this, and the complement of that is 0 is sent on this. That is the voltage sources are switched in such a way that this makes a transition 0 to 1, whereas this goes from 1 to 0. Obviously, the currents will be in the opposite direction here, and hence the voltage here will be positive, whereas this will be negative. And when you do the comparison, comparing this voltage, you will come to know what the logic level is a comparison. So slight change in the amplitude may not matter so long we are following the NMH, that is noise margin corresponding to low and high as such, which also gets reduced if the voltage is reduced in high-speed circuits. But I think what we consider, these are the identical transmission line with same L and same length and all that. And then this comparison will tell you what the signal, what was sent is 1 or 0, and it receives this. So this is similarly, you can implement a current mode differential signaling also. Now, what are the benefits of this differential signaling mode? The signal swing in the, when you have single-ended signaling mode, voltage mode, it was 0 to 1, that is 0 to 1.8. But when you go for differential, it is delta V. One is going from 0 to 1.8, the other one is going from 0 to minus 1.8, or the reverse of that, and hence delta V will be equal to 2V1 minus V0. So it will be double. It means the signal swing here will be twice what it was observed in the single edge signaling mode, single-ended signaling. When the signal swing increases, the noise margins will increase, another advantage. So you can work with the same noise where you were not able to work with the voltage mode signaling. Now you can work because your noise margins have increased. Because of this also, the speed also will increase, the TD will decrease, because it's only now it will be approximately 50% delay what was there in the single-ended signaling. The return current is 0 because it is always return current is, if you see V1 plus V0 by 2 and V0 is minus V1, so return current is 0, so there is no return crosstalk. A very, very important thing here is that there is no return crosstalk noise, and hence it's very, very advantageous and beneficial and advisable to use different signaling mode when you are basically working with high-speed design. No doubt you have to sacrifice on the area and hardware, but from many points of view, most of the things of the high speed, that is high speed as well as the noise margins, will be taken care of. So now let us come to the topic here, that all these things, crosstalk and right-hand crosstalk and all those intersymbol interference we have seen. So from where the noise is coming in the data system. So all these now a system level consideration. So the noise can come from the transmitter power supply or the transmitter offsets. The noise can come from the signal return paths. So this is in the return, you are creating some voltage which gets impressed, and noise is from a signal return path. There's a crosstalk between the neighboring lines, either capacitive or inductive, or because of the intersymbol interference, maybe because of the retention of the memory, inertial delay, and all that. And at the receiver side, could be because of similar to transmitter offset, it's a receiver offset, receiver power supply noise, reference offset. And so these are the various reasons because of which noise will appear in the digital system. Now, there are two types of noise. Basically, one is bounded and unbounded. In the bounded, that is bounded, which can be in your hands, perhaps, sir, you can take some action on. Unbounded is a statistical noise, Gaussian noise, where you do not have any control and can occur anytime. So in the bounded, again, we have two. One is called as the proportional noise source, and the other one is independent noise source. It's also the fixed noise. Perhaps a very little action can be taken on that when the design is done, but here definitely you can have some control. So which is the proportional noise source? The noise source which is proportional to the signal swing. Which are those? The crosstalk always is proportional to the signal swing. Intersymbol interference, signal return noise, signaling power supply noise. All these are proportional noise, because if you reduce the signal swing, these will get reduced. So this is the proportional noise source. One, definitely it is not possible to completely nullify it. You cannot some signal swing has to be there, and hence, however, you can take the action so that you can try to minimize as much as possible or overpower that noise. That is, your noise margin will be better to take this into consideration. The other one is independent, which is coming from where? Is coming from receiver. Receiver is not, is at the other end. Receiver sensitivity, receiver offset, some unrelated power supply. Maybe on this board you are working and another instrument is there, and the power supply is different and the noise comes from that. Some reference offset. So this is taken into consideration. This could be of fixed nature. We do not have any control. So you have to take into consideration in the form of fixed noise. So if you consider no noise budget as such from design point of view, what we can say, if this is the total swing from logic 0 to logic 1, let me say is of 400 millivolts, then your total noise is, which is called as the gross noise, should not be more than half the signal swing. So it should not be. So threshold is at 200 millivolts. And all the noise sources, when they create some voltage, must be within these limits. So this is the gross noise margin. We can work with a 200 millivolt, but there are the different contributions. One is the proportional, which let me say it is 20%. So it is 80 or 200 millivolts into 20% is 400 is a proportional to the signal swing. So 400 millivolts, 20% is 80 millivolts. So this is a proportional. And independent noise source, because of the receiver offset, receiver sensitivity, unrelated supply, is, let me say it is 50 millivolts. So 80 plus 50 is 130. So what is perhaps with design of a design engineer is in hands is this 130 millivolts. But we have said that we can have gross margin of 200 millivolts. It means a room is there of 70 millivolts for unbounded, which is the Gaussian noise, to be within these limits. And Gaussian noise, when it will happen, why it will happen, we cannot say. So we'll have to say that this Gaussian noise, at least with the knowledge of whatever Gaussian noise or the statistical noise, the thermal noise, short noise, the other noise, which can come into picture, is of what level. And this net margin to that Gaussian noise ratio is a very, very important parameter here, which is called as VSNR, voltage signal to noise ratio, which can give you bit error rate. After how many bits error will occur, and this has to be as large as possible. So absolute swing or absolute threshold is not important here. What is important here, after you have done this type of design, what is the VSNR here, so that Gaussian noise taken the worst case Gaussian noise is much less than this net noise margin to give you a very high to give you a very low BER as such. So let us consider this. Now, for absorbing gross noise, half voltage swing, as we have said, must be greater than the total noise voltage. So half voltage swing is Vs by 2, has to be greater than. Now I am considering only the bounded noise, that is the proportional and independent. So proportionality constant is Kn into the signal swing is Vs plus independent is Vni. So if you solve this equation, you will get that is the swing Vs, total swing to independent noise has to be greater than 2 into 1 upon 2 minus Kn, Kn, that is the proportionality constant here, Kn. What does it mean is that you can increase this either by reducing this Kn, that is the proportional noise has to be in proportion, that has to be small, or by reducing this Vni independent. So these are the two things which give us the design parameter. And if you try to see the set operating region here for Kn will be on this side of this. You should not go below this line. Depending upon what is the voltage swing, you will have to decide Kn which is in this area as such. So this I was talking about, that this is the net margin and this is the gross margin. So net margin VNM divided by gross margin gives us a margin ratio. What is the proportion of the net margin is corresponding to the gross margin. Now let us try to talk something regarding how do you find out this noise because of the Gaussian sources. So it's a random noise. So the probability distribution of this we have to take into consideration. As I have said, this will be because of the thermal noise of the component, short noise, or uncorrelated bounded noise sources which are not a part of this, a perpendicular crosstalk, that is, we know that the many lines basically on the multi-layer will have the perpendicular intersect, that is one line goes in the horizontal direction, the other on the other layer will go all lines in the parallel. So there is perpendicular crosstalk and all that. So these are modeled by Gaussian because when they will come into picture and you do not know. Most of these have zero mean. And the relevant parameter of this is a standard deviation, which is root mean square. So several Gaussian noise sources, which may be there considering the worst case, can be modeled using single source with RMS voltage VGN given by summation of VRI, I going from all to different noise sources square under root of that. That's a standard deviation, or the root mean square root of that. So let me say I have two noise sources there having RMS value of 10 millivolts and 20 millivolts respectively. Then I can find out that this VGN in the worst case will be a root of 10 square plus 20 square, which is of 22 millivolts. So similarly, you can find, considering all the Gaussian noise sources, what will be that noise source which will be which will be generated by one single source, which is modeling all the several noise sources. And the VSNR is VNM, net to VGN. That is the noise because of the Gaussian. The other was margin ratio. This is exactly, VSNR is completely inverse of that margin ratio. Here it is VNM, the net margin, which was of 70 millivolts there, and VGN, which came to 22. 70 upon 22 is hardly 3 is the VSNR. If you take the VSNR higher, then is by this expression, the probability that error will occur, this is the Gaussian probability distribution function, is as per as e raised to minus VNR square by 2. And to be very exact, this is basically the approximate exponential function. To be very exact, it will be the error function, 1 minus error function of VNM by VGN. If you see, so this basically is a pessimistic, but if you use this and if you are getting that error, definitely in actual, your error will not be more than that. So in all practical purposes, in the design, it's better to use this. So error function, if you plot both the error function and exponential function and the error function, you will see that a pessimistic will always be taken as a design guideline for saying that if my VNM by VGN, for example, it was 3. So for the 3, the bit error is 1e minus 2. It means after sending 100 bits, there will be 1 bit in error. But if I have higher, that is VSNR is equal to 9, then that is I have 1e minus 8. It is after sending 10 raised to 8 bits, there will be only 1 bit error. And this making VSNR higher is the design we had to do. Excuse me. I'm back. Just give me 2 minutes. Okay. So yeah, understood that. How do we basically take into consideration the various noise sources? And the proportional noise sources basically come from whatever points we have considered since morning, as far as crosstalk is concerned, intersymbol interference is concerned, return signal crosstalk is concerned. So they will come into picture. Besides, there are some which is related with the hardware as such, receiver resistive sensitivity, receiver offset, uncorrelated power supply noise and all that. But beside that, the statistical noise are very important, and in the given net margin, we'll have to see that what is the statistical noise is there should bear a very high ratio, at least greater than 6 or 8 or something like that, to give very low bit error. So this basically tutorial will not go into the details of this, but I consider the three where the percentage, it means it is a proportional frequency attenuation, crosstalk from adjacent lines, reflections taking because of ISA, which add up to give me 0.25. Now, this is a differential signaling. So 250 milliwatt differential signal will have twice the voltage swing. So it is 500 milliwatts. So 500 milliwatts with 0.25 kN will give 125 milliwatts. It means the proportional noise signal noise voltage is 125 milliwatt. Then independent, 20 milliwatt is the receiver offset, 10 milliwatt is the perpendicular crosstalk, 10 milliwatt is the other noise. So it's total 20 plus 10 plus 10 is 40 is coming into picture, which is the independent. So VNI is so this is other noise source is basically the Gaussian. So you have perpendicular noise is Gaussian. So only 20 milliwatts is VNI. So VNI is 20 milliwatts, which is fixed noise, and now KNS plus 20 is 145, which basically is from bounded noise sources. So net noise margin will be half the swing, that is 250 minus 145, it is 105 milliwatts. The statistical noise is of these two, perpendicular crosstalk and other noise. So it is 10 and 10 each. So it goes to 10 square plus 10 square, root of that is 14. So statistical noise, which we call VGN, is 14 milliwatts, whereas the noise margin was 145. It is much, noise margin of 105. So VSNR will be 105 divided by 14, which is 7.4. And as per the pessimistic equation, this BER will be 1.1 into 10 raised to minus 12. It means only 1 bit error after sending 10 raised to 12 is quite good. And this is what you have to get in this in your design. This is one of the guidelines. So question is now, do we need to noise budget for every signal? Of course not. It's very difficult. So noise budgets are done for classes of signals. That is a group of signals that obey a set of design rules or ground rules. So there will be board-to-board signals, intra-board signals, that is chip-to-chip, global on-chip signals, special signals in case of domino or rambit lines. And for each class, we carry out a noise budget depending upon the line, correspondingly decide the line geometry, spacing, for how long the line can go parallel, the ground shields, impedance and termination tolerances, driver and receiver specifications. If each class of signal meets this specification, then the design detail system definitely will beat the noise budget, and it will have a BER at least as good as or even better than the calculated one. So this is what you have to take into consideration. So in summary of these three, what I can say, the parts of my presentation on considerations for high-speed detail design is that high-speed detail design starts behaving like analog systems at high frequencies. The driving forces are what we have seen, And the threats also we have considered all in terms of transmitter line crosstalk, capacitive coupling, inductive coupling, return noise, ISI. Then how the noise we have to take into consideration, how the noise budgeting to be calculated and how to manage the noise. The other two aspects, that is the power supply, that is any detailed design will be as good as your power supply. So you have to pay the attention to this because a noise comes from the power supply. And for that, you have to use ample of decoupling capacitors. Basically, in your design, if at all any noise is there, then it will be immediately taken to the ground. So decoupling capacitors basically will try to clean the signal lines if have got corrupted, and also will act as a reservoir when the power is switched off for certain time till the devices come to stable condition. That is, there is no what I can say, they stable, stabilized to 1 voltage. So these are basically considering these. The guidelines for high speed is reduce mutual capacitance and mutual inductance. Use series termination for transmission line of match impedance. Use differential voltage signaling if you are really considering very high frequency operations. Provide ground at various locations. Increase in rise time possible, keeping in mind whatever bandwidth you want. Separate out digital block from analog block, that we have to take into consideration. Number of signals sharing one ground plane. Plan the noise margin and noise budget so that it doesn't exceed the limits. And freely implement decoupling capacitors have a good power supply. As we know from the first day lectures by industry persons, that the today's keywords, and as we also know that artificial intelligence, machine learning is a keyword, robotics, data analytics, cyber security, pervasive computer. These are basically, you can say, things where we can also work. The hardware can work for that, and also pervasive computing besides algorithm, hardware solutions are required, and still there is no end to Moore's law. It means for all those who are interested can continue working in this area for the various research areas and have their career, because it's not, there's no end as such, and the things will go on improve. The evolution which is taking place after every 2 years, and we have the scope for carrying some research or the work in this area. So from this presentation, I will say the takeaway points will be: what are the transmission line effects, crosstalk, one word, return signal crosstalk, inter-symbol interference, noise margins, BER, and all that. So I think this is the sharing from my side on the challenges as such, as far as some solutions, and we can also find out some innovative solutions further also to take care of. But this will be the sort of what I can say higher level thinking to consider what will happen at that level, and correspondingly giving some solution which will work at very high frequencies. Low power also is an area where I think will be a separate thing at the architecture level and the system level, how we can do that. But I think that also it's in terms of the battery research in the batteries and all that, and other aspects which are yesterday clustered voltage scaling, or having the transistors of various threshold voltage, or clock gating. These are various as far as low power is concerned. So that I'm not teaching in detail. However, we can go for another 45 minutes to my second presentation, which is regarding synchronizing the signal at the receiver. Now, at present, we had seen only on the interconnect. Now we'll see at the receiver how the receiver is going to see whatever has been sent by the transmitter without signal getting corrupted. So what is that eye diagram, and other things will come into picture. So any question is there, you can ask the participants, please. Over to Rathod, sir.
Madam, can I say? Anybody has any questions? Right.
I don't think. Sir,
कोणतरी विचारलंय what is mostly preferred for transmission purpose? नाही, तो ते नाही कळलं मला.
What is mostly preferred? I could not get the question. I think yeah.
Madam, I'll repeat. What is mostly preferred for transmission purpose from one point to another? Current or voltage at high frequency?
differential signaling or current signaling.
Yes.
Because the voltage degradation doesn't take place. There is no question of voltage degradation on the when you use the current signal modeling. The current is same in the loop, and hence current signaling will give you better reception of the logic levels. Or differential is the best, but you have to sacrifice the area. Differential has lot many advantage, and I feel perhaps I recommend sacrifice on the area, but use differential signal because noise margins also are taken care of. Voltage swings are higher, and return, there is no return current path. So the return crosstalk is completely eliminated in a very highly dense circuit. It's very difficult to control the return signal, impedance as such, and hence differential signaling in all respects is advantageous. I think we'll have to ask these questions to the industry persons, what exactly they are using, because these things are never made clear by the industry people to us. These are all from the literature or the papers and all that. But what exactly Intel or those who are working on 3 nanoseconds are using? Perhaps I think this Amey can answer this question. If we correspond with him. Thank you very much. It's a nice question. Any other?
Sir, you can also ask this question to our one of the resource person analog circuits. He is working on current this kind of circuits actually. Research on this. Are there any trade-offs to be observed in HSDD?
Of course, TR and bandwidth is the first trade-off. You have to basically have the rise time and the bandwidth to meet your requirements and correspondingly consider your design. So that is one of the trade-off. And then as we have said, the trade-off again, the previous question, using the proper signaling mode and all the noise voltages to keep it by using deciding on the dimensions, which will not in any other way. That is, you can see that Z0 is given by root L by C, whereas velocity on the transmission line is given by 1 upon root LC. So these are slightly contradictory in the sense, if you work on C only, reducing C will increase capacitance, but then that will reduce, will increase the velocity. 1 upon root LC. If you reduce C, then velocity will increase, but you'll have to keep the same Z0, perhaps you'll have to decrease L by the same amount. So these are some of the, looking at the equations, also we can say what would be the trade-off as far as even the physical dimensions or the material parameters are concerned, which needs to be taken at such a low level. We cannot work with Si and SiO2 and the aluminum or the silver as the metallization, and we have to go for the tungsten and all that, or maybe what I can say is the noble material. This is the, study separately is going on the material aspect as what will be the future materials will be used for the sub nano. Now 3 nano, okay, but sub nano, are we going to less than 1 nano also is a question today, but I think the things are evolving, and let us say that we will face it. So knowing these things, at least at this level today, is very important to face the future challenges or future things which we can absorb as a teacher in the years to come to teach our student what is the current state, not, considering SI and SiO2 parameters. Thank you very much. Thank you, Majeshri Madam. Any other question? I'm happy that some people are interacting.
Thank you, Madam. Thank you.
Thank you. Thank you. Any other question? It's, one more question was there, I think.
Let me see chat box.
No.
Achha, is there any free tool? Is there any free tool for signal integrity analysis?
Sir, no. And no tool of signal integrity in cadence professional, this one. Only the research level tool has this, which is at present, I think 28 lakhs or so. So only research tool has this signal integrity. No commercial tool is having signal integrity analysis. That is what the problem is, that at universities we teach all these things, but seeing these things really becomes very difficult. We can only analytically compute how much it will be. So those who are, those institutes which can afford to go for research, but again, I wanted to ask Cadence that why are you not providing such maybe the different tools which some maybe limited access to all who are interested in this. because we had to cross check with this, but all these simulation tools, signal integrity is very, very great issue for all these designers. And besides PVT, which we can do and have been done, signal integrity at present is present only in the research version of Cadence.
Yes.
So even verification, which is very, very common as on today, that we need to teach verification because scope is there for our students to go in that field. Even that is not, open source. It's like, why I don't understand, why don't they supply these verification things, available system verification on the system to check. Maybe it is not as accurate as industries is doing, but some level of confidence students will have when they work with the tool. So that I think with time, perhaps these will become available. At
Agreed,
present,
madam.
no.
At least limited versions they should provide, no? So that
Yeah. At least what are the facilities and what we can do? Because signal integrity is very, very specialized field as such, and lot of research can be done, but not possible unless you have a tool with you, because it's just impossible for us to, debug these problems where the capacitance is higher, because of it's a cumulative things which we'll see externally, and then at exactly where the problem is, like you see in Xilinx, which is the critical line, is immediately highlighted. This is the critical path, and then you take action on this by changing the code so that your critical path will get reduced and you will work at higher frequencies. Such type of indicative tools have to be there for debugging purpose, and hence testing and testability also is a very, very important issue in VLSI. Actually, I would like to tell these participants that VLSI design, though last 3-4 I think lectures were mostly concentrated on microelectronics and CMOS, is a part of that. Many things can be done at the system and the architecture level, where perhaps I think as engineers they will have interest not in CMOS, but they will have interest in doing the design at the architectural and the system level, perhaps where we should put more efforts and try to give those things to our students. Generally the reluctance is there. VLSI design, it means CMOS, and CMOS, they don't understand the complete reluctance that they will not learn through that. But VLSI today is not restricted to CMOS. CMOS is only, I can say, 15 to 20% part of that, doing something on the chip. It doesn't contribute overall for the entire speed or the power as such. It's only a small contribution from that large contribution where you go to the PCB, joining two PCBs or connecting interfaces and all these things. Basically, no, we haven't taken into consideration at the interface what will be a sort of inductive impedance coming into picture, but that will be quite large and much, much higher than what comes on chip. So chip is only one thing basically. So those who are not interested in CMOS need not get repelled from the VLSI design. Lot many things, 80% of the VLSI is these in higher abstraction levels. So that is what I want to emphasize on the minds of the participants also. Okay, sir, I think, can we go for, because I think I'll need 45 minutes.
okay, ma'am.
So I'll share another screen. I will stop sharing this. You are sharing, you are streaming, how to share. Stop sharing. Okay.
But yeah,
Yes,
on top, madam, there will be.
yes, got it. Got it. Now I will have another.
Madam, I want to ask one question. My
Yeah,
PhD
sir.
student is working on this signal integrity issues at PCB level. And
In the
PCB, at PCB levels, he is working on signal
yeah,
integrity
sir.
codes.
In fact, if you see the book by Black, it
Book
mostly
by Black.
concerns about the PCB level. Book high-speed digital design by Black.
Acha.
It devotes most of the, contents on
Acha.
PCB level design only. So these things,
Acha.
these ideas, whatever I said, can be extended to the PCB by considering the materials there and the their
No,
things.
madam,
See,
madam, what I want to ask is, she has got there is a source and there is a destination in. At destination, when the signal goes to multi-layer, she is observing a eye diagram as a performance parameter. But then she is able to get the eye diagram for single layer. But when she goes for multi-layer PCB, she is not able to get, because the vias and all those are created, and she has got somehow stuck up at that particular point. How to get the eye diagram? So is there any other way out?
Sir, I will just suggest, looking at
Okay.
whatever was the inertial delay and all that. In her interconnect, let her put one, inverter, and give some 1 kilo ohm resistance in feedback and connect it. That is just the feedback inverter. That is just the inverter with the 1 kilo ohm feedback input to output, and try to see that. And perhaps the size of that. Is she doing at the chip level? Is she doing
No.
it? No.
No.
Can she insert any device in between?
That
The
no,
interconnect and the receiver?
actually she's how she's working. She's working on HFSS antenna tools, right? And so kind of a multi-layer PCB using metamaterial structures, so that when signal from one layer to another layer, the signal integrity issues will be resolved. It's like that. So at one point she inserts a signal, and another point she observes the eye diagram. One single layer, she gets an eye diagram, perfect eye diagram, but as soon as you move from one layer to another layer, she doesn't. So,
this is what I was trying to say, that if because of the bundle of wires, the crosstalk and this noise, total noise, whatever we have considered, is exceeding, that is the eye opening is not there at all. She may see some lines there, but the eye opening will not be there. Is that so? Can we see some sort of run pulses there, or some sort of going from one but not to zero?
She's not getting only eye diagram. She doesn't know how to get eye diagram for multi-layer PCB. So is there any other way she was finding out? Other way of measuring the signal integrity performance? It's like that.
No, sir. Eye
It is a
diagram
tool-related
only
issue.
is the
It's a tool-related issue, but then we have to overcome that problem. No, she's not able to do it.
No, when we interact with the industry person, they always insist on eye diagram.
Yes.
Perhaps we can contact Ravi Kumar from Texas for this, because he is working on that, very much on these eye diagrams. Perhaps I think some information can be obtained from him. If she is finding some problem, I can pass on his email ID to you, so that you can.
Madam, somebody has asked a question. Is there any other reference book for the signal integrity?
Yes, not signal integrity, but the complete detailed system design is by Dally, D-A-L-L-Y, Dally.
D-A-L-L-Y.
It is detailed system engineering, and it is available online. Online in the sense soft copy is available, PDF copy is available.
Digital system engineering. I'm writing in chat box. Digital system engineering, no? Okay.
By William Dally and John Poltron. Should I write it in the chat box?
I wrote it, but I don't know correct.
Yeah, William Dally and John Poulton, Polton.
You can see if it is correct. Oh, sorry.
I'll share my screen first.
No. Okay. Share, madam, your screen. Go ahead.
Yeah, I will close the previous screen.
It has gone to special everyone.
Share. Microsoft PowerPoint. Yes. Are you getting it?
Yes, ma'am.
Yes. Okay. So any other questions, or should I go further? This is 12:30. I think by 1:15 we'll be in a position to complete this.
Okay, ma'am.
So I
full screen करून टाका, madam.
Full screen करून टाका. Yes. Okay.
Okay, go ahead, ma'am.
So again, a very interesting topic regarding synchronization and synchronizer. I like this topic. I mean, students also will feel interested, because some architecture level things are there. So again, the same model, TX, RX. Now, basically, we are considering the full transmitter. No doubt the interconnect is there, but receiver has to receive the data which has been sent, at least the logic levels as such. TX has been driven by the TX clock, transmitter clock, where RX is driven by the RX clock. This clock may be the same, that is derived from the same signal on a crystal, or may not be, or there could be a skew between the two, so there is some phase difference, or a completely from another crystal, which basically may be having the same frequency, but a slight phase difference. So which will add cycle after cycle and will go to 360 after n, and then there is there is no synchronization as such. So what we want is that the data transmitted by the transmitter clock is received maybe after delay, maybe n clock cycles by the receiver, which is on the receiver clock edge without any problem. So this basically is something. The synchronization is the data received by the receiver is synchronized to the receiver clock. It's transmitted by TX, but it's synchronized by the receiver clock. Hello? Any question? Okay. Okay. So what are the possibilities as far as this frequency and phase difference in both clocks is concerned? How to attain the reliable reception of data transmitted by TX by RX? The data is transmitted by TX, but we have to receive it by RX. So this needs to be synchronized with the receiver clock. And how to synchronize the data arriving at the receiver by the RX clock. So some of the guidelines, these are the objectives of this presentation as such. So this is organized as what are the classification of digital circuits, as you know, sequential, combinational, what is D flip-flop was stored, but I'm going to go to the timing parameters of the D flip-flop, which are very, very important when we are working with the high-speed circuits. Then synchronization, there could be a signal. See, this, I mean, on your design, the signals are coming from some other equipment or some other circuit, and they will not, they are a synchronous signal. Your clock at, I mean, you are transmitting something with transmitter clock, and the signal which is coming on the D flip-flop, which needs to be registered by D flip-flop, it's asynchronous with this, can come at any time. You do not have any control. So in that case, how do you synchronize that with respect to the transmitter clock is by means of the brute force. It's brute force. That is, you have to force it to synchronize. But in that case, a synchronization failure can happen where the output can go into the meta state, and how much it will remain in the meta state, we do not know. So there will be some sort of, that is, you do this, there are some solutions, we'll see that. Then there are the periodic synchronizers, basically mesiochronous synchronizers and plesiochronous. Mesiochronous, it means the clock is the same, but there is some constant phase difference. Which constant phase difference can be basically seen at the initialization stage, and you do some solution only once in the lifetime and give it to the customer that this is, now it will work, and then it becomes synchronous. The receiver also will receive it on its clock, which is synchronized with the TX. Or the other one, as I have said, where slight difference is there between the two signals as far as the phase is concerned, the slight difference in the phase. And here we'll have to have a FIFO synchronizer with flow control also. That is, when the cycle winds up, when it goes, the phase difference goes to 360 or maybe a safe region of 270 degrees, then you try to resynchronize it again. So this was, resynchronization was not here, but here it will be there. That also is a part of the design. Once you give, after that in resynchronized cycle, that signal will be generated when the flow control will come into picture, either to replicate the symbol previously received if the receiver clock is higher than transmitter clock, or I mean omit the signal so that repetition is not there. So this we'll see as plesiochronous. Then asynchronous FIFO basically will do this job. And there are some self-time circuits, which are the asynchronous circuits, and the conclusion. So we know combination. I'm not going to details. You know all about FSA, Mealy, Murray machine and all that. So flip-flop is one of the important components, and clock is one of the important signal as well as the sequential circuits are concerned. Generally, I think we can consider positive or negative, but how we describe its behavior is by means of this diagram. That is, this is the clock running, a periodic clock, maybe 50% duty cycle. D can come anytime, so D will have any type of at a transition anytime from 1 to 0 or 0 to 1. However, D will be sampled only on the rising edge of the clock. By keeping, that is, this will be sampled faithfully if at all this D is stable for a time corresponding to the setup time, and D is stable for a time corresponding to the hold time. And this is called the summation of the setup time and the hold time is called as the aperture time of the flip-flop. And this needs to be taken into consideration as a specification of the flip-flop of the technology you are using for choosing the components for your design. Beside that, if these are obeyed when the clock is rising, D was stable for time corresponding to the setup time. Also is not changing for a time corresponding to the hold time. Then the Q will be as per D. So it was 1. So this will be 1 after a time corresponding to propagation delay low to high, which is clock to Q time. After the rising edge of the clock, it will respond to D with these restrictions only after a time corresponding to the propagation delay low to high. Similarly, there will be propagation delay high to low, but it is clock to Q. Now here, if you see, this is the next rising edge of the clock. Then this basically window corresponds to the aperture window. And before this aperture window, the D is stable. After the aperture window, D is stable during this aperture window with respect to TS and TH, and hence at that time 0 is there. That 0 is passed on to Q after a propagation delay. So faithful, passing of D to the Q will happen if this restriction is observed. And this is a positive edge trigger, so only will happen on the positive edge of the clock. Between the two positive edges, even though D changes, it will not be passed. So some reliable, operation is there of the D flip-flop. But now you come to this, because D can change anytime, and D has changed here. Now the next positive edge of the clock is here. Now within the aperture window, though a hold time restriction is followed, setup time is violated, and hence the output which is coming after a propagation delay, but which is unknown, is X here. Similarly here, with respect to this rising edge, again the whole specification is not observed, so again this will continue. So uncertainty is there in whatever you sampling if these restrictions are not followed, and hence one will have to consider what is the setup time specification as given by the foundry and the hold time specification, which gives this window to the, with reference to this rising edge of the clock, so that D which was stable before and after that only will be sampled. It means there is predictable behavior of the D flip-flop. So as you can see, this is D. This could be D is not only one line, it could be a bus as such. So this D, whatever were the bits on this, were stable during the aperture window, and hence you have this after a propagation delay. Here also it is stable, so it has gone to the has been sampled properly. But this sampling will be with respect to the rising edge after a time corresponding to the propagation delay. So this is, and that decision window, what you have seen in the previous one, is basically called as the meta-stability decision window. If you do not observe this, if the D input does not observe this, then this output goes into the meta state where this type of behavior on the waveform is shown. So this is called as the meta-stability decision window. Now here you can see that here this D was unstable in the window, and hence you have seen that after a propagation delay, the output has gone into the meta state. And with respect to this clock, now for how much time it remains in the meta state depends upon another parameter of the flip-flop, which is the meta-stable recovery time, is called as a tau RS or tau RSH. This is a meta state. Again, this specification is not in our control, it's the foundry specification. So one has to know this specification also to decide what should be the clock period. That is, if clock period takes care of this meta state, even if the output goes, but the clock will arrive only after this, then the output of that flip-flop will be stable, otherwise not. So these are the two parameters one will have to take into consideration when you go for the high speed. So as far as classification of signals is concerned, asynchronous signal do not have any frequency, can occur at any time. The phase difference is arbitrary. Two signals are said to be synchronous if they have the same frequency, they are in phase. In the phase of 2 pi also is okay. It's not 0 degree phase. phase of multiple of 2 pi also is okay. That is, the age of another signal is occurring exactly at the same time of the age of this signal, positive age of this signal. Mesochronous frequency is same, both of 100 megahertz, but there is a constant phase difference of maybe 1 degree or 0.5 degree. Plesiochronous, constant phase difference of 30 degree. And plesiochronous is the phase difference, a slowly varying phase difference. But if I say it is 1 degree phase difference to start with, then in the second cycle, it will be 2 degree. In the third cycle, it will be 3rd degree. And like that, after 360 cycles, there will be 360 degree phase difference. So depending upon whether the receiver clock is faster or transmission clock is faster, one will count n, whether the other one will count n minus 1 only. So this we have to take into consideration. This is a plesiochronous, where the flow control also is necessary. When such type of thing happens, when the phase difference winds up to 2 pi, then we have to take some action. Periodic, the frequencies can be different, and there's a periodic variation. When we say periodic, basically is nothing like n times t. That is, the period is, you can, this will occur at regular intervals of time. So let us consider the asynchronous signal, where we are going to use brute force synchronizer, and this generally is, you can use arbiter also or self-time circuit for this. This generally the most of the designs, yesterday also asked this question, and they said that most of the designs here are synchronous only. That is, the tools have been developed to take care of the synchronous design, but the era of asynchronous, because they will work faster if the design rules are taken into consideration. So to still go to the higher, perhaps we may have to design asynchronous digital signals with asynchronous signals. Where self-time circuit, that is handshake circuits, will come into picture. If signal is synchronous, you can directly sample signal with clock. Very close vicinity, transmitter and receiver. So the clock age occurs almost at the same time. Now, almost at the same time also is a very crude term, I can say, in digital circuit, because how close we can say femtoseconds, picoseconds. So that again depends upon at what bandwidths we are considering, at what frequencies we are working, and what is the TRSH. But if it occurs almost at the same time, perhaps you can sample it directly. Mesochronous signal, as we have said, a constant phase difference is there. And the delay element either in the signal path or in the clock path will do the work. Plesiochronous, as we have said, flow control. And we have to use an asynchronous FIFO there for, storing the bits or the symbols. So let us see the brute force synchronizer. So this is a signal. It's coming from anywhere. I do not know when it will come. But now when I'm taking it to my system, I will register it using a flip-flop, a D flip-flop, having that setup time, hold time, recovery time, parameter specification taken into consideration. This is the clock. And this clock is also going to another flip-flop, maybe at some place, having some skew, and hence having some skew or may not have. Some skew is tolerable or will occur at the same time. But now, most of the time, if IFSI is stable, taking into consideration decision window, output of this will be stable, no problem. And then it will go through this table. Again, it follows the decision window of this, and this will be synchronized signal. But once in a way, it will happen that A is unstable within that decision window, and signal here has gone into the meta state, and this we call as AW. That is, this A has occurred almost at the same time at clock without, taking care of the decision window, and hence AW doesn't go to the logic level, full logic level, but goes to a level where slowly it recovers from that and goes to the final full level before the next cycle age comes. So AW can have a behavior, if seen, will be something like this. However, will be stable again within a decision of, window, considering the decision window with respect to next clock. And this is a pipeline approach. This table will be then sampled by this, and you have sampled or the synchronized with respect to clock. So thus asynchronous signal can be synchronized. This is nothing but two flip-flops in series is nothing but a brute force synchronize. We are trying to synchronize the signal with respect to this. However, it could happen that even after this, if the clock is faster, even after this will be still in the meta state. Still, this is not yet fully recovered, and that is we call as the synchronization failure. We are implemented the brute force synchronizer, assuming that for the next clock, the output coming here will be synchronized with the clock. No doubt, with respect to A, there will be one clock latency as such, but it is synchronized. We are happy with that. But this could happen, this may not happen if the clock is fast. And hence, within one clock cycle, that is, if TR is not taken into, that is, clock cycle doesn't take into consideration the recovery period here, then this will happen, and that is the synchronization failure. What is the rate of that? That also will work out. I think all of you know about metastability. Rod-sir, do I need to explain this? Metastability?
Madam, I don't know. They should say.
Okay, what you can see is that the output of the first flip-flop can, the worst case can go at this. That is, after that it samples, it is at this. And again, because of the RC coming into picture, exponentially it will reverse. So there are the exponential pattern which will recur to the final. So considering this worst case, that is the worst recovery period is this, considering that after the first flip-flop, it is at this level. If it is at this level, it will recover fast, no problem. But then there will be some, it will be stable within that decision table. So taking this, that is the two inverters, that is any flip-flop, basically D flip-flop is built at the transistor level or at the physical level using a transmission gate and the two back-to-back inverters like this. I'll not go into the theory of that. You have understood that if at all the first flip-flop output is at this level, after that is being sampled, then it will minimum, that is the worst case scenario is that it will take maybe 200 or 300 nanoseconds. Again, this period, that is this you can see, here it is recovering. And you will have to give the cycle time accordingly. The frequency will be decided by this. These basically are the VTCs or back-to-back this one. And then how, if it is at the meta state, it will not recover. We cannot predict when it will recover. But if it is slightly above or below, it will go to a logic level 1 or 0 and will recover from that. So this basically, I think all those who are teaching CMOS and the inverters know about metastability. So this is what I have said. Now, this is the failure as such. Now, what has happened is that the output of the first flip-flop has gone into the meta state, which is, let me say it is VDD by 2, exactly at the center. And then even when the next clock comes, it doesn't recover from that and remains as VDD by 2 only. And this is the failure. Even though you have implemented brute force synchronizer by having two flip-flops in pipeline, assuming that the output of the second flip-flop will be synchronized, but it may not happen if that point is at the meta state after a waiting time corresponding to the first, that is one cycle time. And hence, the probability of failure is that probability that enters into the meta state and the probability that still it remains in the meta state after a waiting time. Now, you have to give some waiting time, and this waiting time in case of synchronous designs is going to be 1 clock because you are waiting for the next clock to come. So waiting time is corresponding to 1 clock. So the probability of failure is that the flip-flop enters into the meta state, which is PE, and it remains in the meta state even after this one cycle is over. So, I mean, this is, how do you calculate probability of this occurrence that it enters into the meta state? That this is the time during which D changes, it can go into the meta state. But what is that probability? The total cycle is there for the D to change, and it is changing during this. So the probability is nothing but this decision window TA divided by TCY. So the probability that it enters into the meta state is only TA by TCY, that is TA into 1 upon TCI is FCLK. So if you know the aperture window and you know at what frequency you are driving your system, then you can find the probability that enter. Simple consideration here. Then even after waiting time, if initial voltage difference is too small, like this here, is the initial voltage is too small, and then it will exponentially will rise to either the logic 1 or logic 0. But even after this waiting time, it doesn't recover. Then it is basically, again, what is the initial? If the initial difference is, large, then it will recover fast. But the initial difference is small, it will take longer time. And hence, this probability that it remains in the beta state is given by what is the initial phase difference to the final. Final, what we want is that it has to go to the true logic level. So it's given again by exponential of minus TW, 1 clock cycle period, divided by its recovery time, the meta stability recovery time. So it's given by this. And hence, the product of they are mutually exclusive events, and the synchronous failure probability is given as multiplication of P into PS is TA into FCLK entering into meta state, remaining in the meta state, and 1 upon that will give you the synchronization failure, which is basically it's PF, but FD is the data arriving at that. So the event can occur on each and every data being sampled, and hence it gets multiplied by the data clock. Generally, data clock will be much smaller than the system clock. So FD into PA. So this basically is an expression to find out the synchronization failure frequency. And considering some example, I think I had tried to find out data arrives at 20 megahertz. So the data period is 50 nanosecond. System clock is 200 megahertz, 10 times higher than. So waiting time is 5 nanoseconds. Aperture time for the flip-flop chosen is 100 millisecond. And recovery time is 170 picosecond. So if you try to work out that, you will find for these parameters, the failure is 0.5 years. It means your system will fail after only 6 months. Is very much sensitive to recovery time. So if you consider the instead of 170 picosecond, if you consider 150 picosecond, then I think it has gone the other way perhaps. If it recovers fast. If the recovery is fast, then it is quite large as 20 years. On the other hand, if the recovery time is large, it will be few hours. So beta stable recovery time should be small, which puts a constraint on your clock also, and the failure will not be there. So this is a very, very sensitive to the recovery parameter. If it is small, okay. If large, it's bad because it doesn't recover before the next cycle. I can take another example where the data rate has been the clock rate has been increased, TR has been considered 100 picoseconds, and then it gives on immediately after 6 minutes it will fail. That it's hello. Okay, so this is brute force synchronizer, and we have to consider these parameters, the flip-flop parameters, to find out whether it will fail or not, and then correspondingly restriction comes on choice of a D flip-flop from the technology or the clock period as such. So now there are two parameters what we have to consider when we comparing two synchronizers. One is the probability of failure, the failure or frequency as such, and other is the delay as such, because we are introducing one flip-flop there and beside the waiting time. So the delay of a synchronizer is waiting period which we have given for it to recover. There are two flip-flops there, so propagation delay clock to Q, because it will be sampled only after the clock. And in general, the synchronizers implemented using flip-flop will have average delay as TCY by 2, and why it is will become from this. Either it will be sampled here or will be sampled here, of course taking into consideration the decision window, and hence the sampling could be with almost 0 or with total clock cycle, and hence average delay of a synchronizer will be TCY by 2. So for any synchronizer using flip-flop, this will be the inherent synchronizer delay, which is TCY by 2. So the synchronizer delay in the previous case is waiting time you are giving, which is 1 clock. Clock to Q, because of the 2 flip-flops, it is 2 times, and this is the average inherent synchronizer delay. So these are the parameters used to check the synchronizers. Now again we come to the same and the eye diagram. So now this is what we have. So the transmitter has sent the data. Now it has reached the receiver. When seen in the eye diagram, you have something like this with eye opening amplitude wise like this, and the timing wise you have to consider the timing is only again rail to rail. That is, this is the time, not this cross to cross, but by reducing TR by 2 and TH by 2, TF by 2. So it is the rectangle you have to consider. I mean, if I consider here, this is the window you have to consider that for the timing also. So timing is this to this. So now, if you can align the edge of the receiver clock anywhere here without taking into consideration, then it could so happen that we are not giving, maybe on one side timing margin is small, on the other side timing margin is large. So the best way is to align the edge of the clock, receiver clock, exactly at the center. So on both sides you have equal timing margins, and that timing margin, as was what we have said, by taking into consideration the noise budgeting. So the design on the at the receiver side will be adjust the clock. Now how to do that? We'll see that by aligning it exactly at the center of the eye diagram. So everything checking using eye diagram is very, very important when you deal with the high-speed circuits. Okay. So for reliable synchronization point of view, monitor the I'm opening to be more than the minimum allowed, which will be again trade-off between rise time, bandwidth, time constants of the flip-flop, RC, LRC, everything. Maximum timing noise margin can be obtained if the sampling of data is done at the center of the eye. Hence, adjust the edge of receiver clock to be at the center of the eye so that metastability problem will not arise. So logic levels, the amplitude, and timing levels, it is the aperture time. So this is the brute force. Now let us consider the periodic, which are basically mesochronous and plesiochronous. The synchronous have been taken care of in the previous case, which is a brute force, because the clock was the same. Okay, and the similar thing, how to receive it at the receiver, has been handled. Let us consider mesochronous. Actually, synchronous clock, if there is no phase difference, it becomes a very, very easy thing for one, but which will not happen in practice. You will have to deal with these type of the signals. So can we, now there we're waiting for, that is the total delay, TW was coming into picture. Can we get rid of timing, that is waiting time? Yes, by using the periodic synchronizers. The signal sample by transmitter clock, and then transmitter is synchronized to periodic receiver clock, and then we have a periodic synchronizer. What is periodicity we mean? So we know in advance if the signal is safe to be sampled at a given RX clock edge. Now this is one of the things that we have said, that we need to sample, we need to adjust, align the edge of the receiver clock at the center of this. And we sample it when a safe signal is, generated. Now, if it is safe, we sample the signal as it is. We need not have to synchronize it. But if it is unsafe by the hardware, which we will see now, then we have to make the signal safe either by using mesochronous synchronizer, that is doing either including a delay element, which will be done only once in the entire design cycle, or in parallel while sampling the data, which is plesiochronous. So let us see mesochronous signal. I'll go to the diagram only. Okay. So what is delay line synchronizer? This is again the clock, which is the transmitter clock. And this is the data which is coming to the flip. This can be a number of flip-flops like this, receiving the bus of the data as such. I've taken, for example, only one line. Now, I can measure based on my interconnect and all the components coming into picture and all that. What is this delay that is of this all the thing? What are the propagation delays of the interconnect and as such. And I try to basically delay that by a variable delay line. Try to put we'll put a variable delay line having a delay by which this data should be delayed so that metastability doesn't occur. So if the signal is unsafe, it means it has occurred in the decision window of this. In that case only, you delay it by this variable delay line so that the signal gets delay and the problem of that occurring. No doubt it will be basically sampled on the next clock, but the metastability period state will not come into picture. So this is the solution as such. But this will be done only when you get a signal which is safe or unsafe. Now, what is the delay here? The synchronizer delay, which is the parameter, the comparative parameter between the two synchronizers, is what is that variable delay dV plus once it comes d to q, and since flip-flop is there, it is the average synchronizer delay, which is TCY by 2. So this is the delay of this. Waiting period is not coming into picture here. So let us see now how you are going to how it will be detect the unsafe signal and make it safe. So this is what I can say, the sample. Now what that hardware here is the X, which is the signal, that is the data coming, is given in parallel to the two flip-flops in parallel, that is D and T. One is basically getting a clock, which is we call as the late clock, that is which is delayed, again using a delay line by an amount considering the whole delay of that. We know this because we are using the flip-flops, we know this. So we can put a delay element giving TH delay, and hence this is late. On the other hand, this lower flip-flop is clocked by a clock which basically advance by TS. So TC, setup time is before and hold time is after. So this is the late clock and this is the early clock. Now let us say that X is stable. Even before the setup time and after the hold time. Stable, it means, let me say it is a one level. So when you are sampling, one will pass here, and even at this, we are passing one here. So 1, 1 will give XOR at 0, and this is 0. It means unsafe is 0, it means it is safe. Unsafe is 0, it means it is safe. On the other hand, if at all X is changing from 1 to 0 or 0 to 1, the XOR inputs will be exclusive 1. That is, one of them will be 1, and then this will be 1. And when this clock comes here, which is after done waiting, that is after TW. So we are basically delaying this clock by TW and then checking it. And then even after that, if this signal remains at 1, it means the transition has taken place during the aperture time period of that data of this clock, and hence it is unsafe. And if it is unsafe, then the data which is delayed by TK naught, that is TS plus TH, aperture time, will be taken here, which is XD, but it is safe when unsafe is 0, X will go directly. So each and every time, at every time, we do not have to delay it to make it safe. Most of the time it will be safe only when it appears within the keep out period, is called as the keep out period also. Then only the delayed data will be taken and will be made safe. So this is the basically the principle behind this. So now, extending this, now if at all we try to put a delay line in X and it is a 32-bit data, we will need 32 delay lines like this. The hardware also increases, and we'll have to adjust it to the delay of each line in which it is there. On the other hand, if we put that delay line in the clock itself, we delay the clock by TK naught before it goes to this, that is, one is as it is going to the clock and the other one is delayed by that. And the same thing will happen that if it is safe, that is, it is stable even before, that is, this is, and you are trying to basically read this D after a keep out period, so it will be safe. So if at all it occurs within the keep out period, this will sample it, but if it is not, then it will be directly sampled here. The data is arrived here, whatever it is, But depending upon the safe or unsafe, if it is safe, then this will be sampled, this will be taken by the multiplexer as the synchronized. Otherwise, it will be, it will be taken. That is depending upon this. So instead of putting the delay line in the data, you can put it in the clock and delay it by keep out period and take the decision based on whether the unsafe period, for which we have to use this type of hardware, whatever we had seen by using this, and then. So it's basically a sort of architecture level solution where we can synchronize the data with the clock. Now here the synchronizer delay is one more term is getting because of the multiplexer coming into picture. We have TD mux, TCY by 2 is the average. Clock to Q is definitely whether this is selected or this selected, clock to Q period is going to be there. But now this keeps an eye when this event occurs. So TKO times, because TKO is the keep out period, and the probability that lower flip-flop will be selected is again TKO upon T, similar to probability that enters into the meta state. So TKO times TCY. So TKO times into probability is TKO square upon TCY. So the parameter of synchronizer delay is given by this equation as such, and you can find out that. No doubt multiplexer delay and this is getting added, but you have a simple and lower hardware here to synchronize the mesochronous signals, mesochronous signal having a constant delay. Now, this is again a FIFO synchronizer using 2 registers. Now you can see there are what you have again is a transmitter clock here. This is the transmitter side and this is the receiver side. The clock is L, this is the receive clock. The data is coming here on the D flip-flop of 2 FIFO synchronizer, 2 register FIFO synchronizer simultaneously. One is enabled. Now this you can see the ring counter. The ring counter is there on the receiver side also. This ring counter on the transmitter side generates XP, that is the transmitter pointer, whereas this generates RP, which is the receiver pointer. Receiver pointer is selecting one of the two of this X0, X1, depending upon what its value is. And this transmitter pointer is selecting basically either this or one, that is the enabling of this is done alternately, because if initially it is 0, next it will be 1, 0, 1, 0, 1. 0 will select this and X will be sampled by this, 1 X will be sampled by this. So alternately, this X is sampled by the top flip-flop and the lower flip-flop. And then RP generally will lag one cycle behind this XP. In the design, one will have to see that RP lags behind XP by 1. It means when this X is getting sampled by this flip-flop, RP will sample this X1, which was sampled in the previous, and it gets 1 clock cycle to come out of the meta stability period if it has gone into it. So this is a design parameter as such, that is one will have to see the count of RP. That is when this is counting 1, this should count 0. When this is counting 0, this should be count 1. And then whatever was stable is being sampled. There may be a combinational logic here or may not be, and then given to a D flip-flop, which is clocked by the receiver clock, and you get the data, X data, synchronized to a receiver clock, and where you adjust the clock, edge of this clock to the center of the eye diagram. So all whatever we have learned so far is coming into picture here, where you have some architecture which can basically do the synchronization, which is of 2 signals, X and clock, which basically have a constant phase difference, and hence we can take some action on this. If you see the waveforms of this is my transmitter clock. Now these 2 FIFO FIFO register is a special case where now for this flip-flop, we are considering this may fail when the phase difference is less than 180 or is very close. That is, there is very small phase difference. But let us see the waveforms when the phase difference is 180 degree. So when transmit clock is going like this, the receive clock is exactly opposite of that. So now this transmit clock generates XP at 0101. So every alternate cycle, this X, which is coming as ABC, this will be sampled here when XP is 0 as A here. That is, with respect to this clock, you sample A here. Then on the next clock, you sample B here. On the third rising clock, C is sampled by this. D is sampled here. So X is sampled alternatively as X0 and X1 at the output of the first, the flip-flop, which are enabled by XP at 0 top 1 by low. And hence what you see is that now A is stable here for 2 clock cycles, B is stable for 2 clock cycles. So any data sampled at X0 and X1 is going to be stable there for 2 clock cycles. So even if it enters into meta state, 1 clock cycle will be, the timing margin is there. Okay. But what care what we had to take is that RP has to lag behind by 1. So when XP is sampling, that is 2x0, it should be high. And then when you are considering that when this clock is going high, you are getting this A. That is, when it is stable for 1 clock cycle, RP is going to sample it as A, taking from X0, then from X1, then from X0, then from X1, and like this. Again, you have the serial of ABCD coming at the receiver without any problem, and the clock is the same, or frequency is the same. Phase difference was there, but has been taken care of. So this is okay. The delay here is that of 1/2 CY, as we have said. Only one flip-flop coming into picture, so D clock to Q, and multiplexer coming into picture, and there is no penalty due to keep out period here. So problem is there when XCLK and this RCLK are nearly in phase. They have very small phase difference, and then the timing margin, what one will have to keep, that T lag, that is how RP should lag behind XP, is given by a clock time plus the timing margin, as we had seen in the previous presentation, how to calculate this timing margin. This should be less than T lag. So T lag should be more than 1 cycle plus timing margin. And considering N register FIFO synchronizer, N times CY, that is, it can get sample after N cycles by leaving a margin of TM. So RP should lag behind XP by having this type of the restriction. And this, for a 3, if you go from 2 to 3 FIFO synchronizer, it will come to 2 clock cycles as such. That is the timing margin of 2 clock cycles. Let us try to see 3 flip-flop. Now this is a ring counter, which is 1 hot, giving you 1 hot counter as a, that is 001, 010, 110, and enabling is done by these output of this. So this will be enabled when XP0 is 1, and will not do any sampling till the next 2 clock cycles, and similar thing for this, for all other D flip-flops also. That is, the output which is sampled here, either X0, X1, X2, will remain stable for at least 2 clock cycles. And hence, when this RP is sampling here, again, which will lag 2 clock cycles before this, that is, when this is sampling this will take the X1, which was before 2 clock cycles. When this is here, it will take X0, which was stable for 2 clock cycles. And hence, again, the lag of RP behind XP needs to be, there has to be some hardware basically to adjust this RP value. In general, RP will get incremented, but if at all there is some, proposing, here it will get incremented like this. So this is a sort of hardware for 3 FIFO synchronizer. So you can see when XP is 2, it should take 0 as RP, When XP is 0, it should take 1 because RP is lagging behind this, and that lag has to be of 2 clock cycles. Using that equation, this lag, that is, these three-phase FIFO synchronizer will provide stable and correct output as long as this phase difference is minus TCY to TCY. It means it goes from 1 clock cycle before this receiver clock comes, or 1 clock cycle after the receiver clock. Let us see the waveforms here. So again, you had transmitter clock, a receiver clock. Now we can say they are almost in phase. X as such is giving A, B, C, D on the transmit clock. When the clock comes, it is giving the data. Now X0, X1, X2 from that one hot recounter will be selected only, only after that. Once it's selected, it will be only third cycle. So A selected here X0, and then B here next clock, C here by X2, and then it goes here. So every third cycle, this sampling will be done on these 3 flip-flops. RP, as we have said, has to lag behind by this, and hence A, you can see here, is not sampled immediately on this clock, but giving a room of 1 clock cycle, because RP then selects this A here, which will be selected here, and hence you can see the period of A here, which is the output of the flip-flop, is within this, which is giving a timing margin of 1 clock cycle before this and 1 clock cycle after this. And this definitely will solve the problem of synchronization. We are giving enough rope, and there is no need basically to go to 4 FIFO or N FIFO synchronizer. So this is how the mesocronous synchronizers will work. Now we go where the phase difference is almost, where there is a phase difference, initial phase difference, which goes on accumulating with number of cycles. So this is also, what we have to incorporate here is a phase slip detector. When the phase winds to 2 pi, we have to put some detector here, and that will come into picture. So TX clock, let me say, is 5 megahertz. RS clock is almost same, because when you are using the crystals, they will not be exactly same. They will be almost same. For example, this will not be the difference of 50 KSH, but for the example I had taken is 4.95 is the receiver clock. So there is a difference of 50 kilohertz here, which will account to 3.6 degree as an initial phase difference. So initially itself, when you start your system, the clocks will start, but this with 5 megahertz, this with 4.95 megahertz, giving in the first clock cycle a phase difference of 3.6 degree. It means after a count of 100, you will have a phase difference of 360 degrees. And to take care of this, you can use any of the mesocronous synchronizer which is discussed now. Again, 3 FIFO will be better, with some modification to take case of this phase slip detector when it wraps to 360 degree every time. So after every N, you'll have to resynchronize it. Additionally, you need a flow control. It means what it should do when, okay, it has detected, what it has to do. It has to either duplicate the symbol received, depending upon if receiver is slow, or drop if receiver clock is faster. So this again needs to be incorporated into it. So when we consider the plesiochronous FIFO, you can see the architecture is same, except that some synchronization circuit is coming into picture. Mesochronous was like this, and plesiochronous is like this, with only one, where you are trying to basically XP, which goes to the synchronizer and comes out of this, which is given to ring counter to generate RP. It means RP is resynchronized with respect to XP by the resynchronized clock. So this is what is needed to be done. So either, I'll not again go into the details of this flow control and all that. I'll show the architecture. So this is what it comes into picture. That is as far as incrementing RP in the general case. So this is your RP, or the RP which is rotated, that is one hot output of this, you are rotating by 1 or 2 so as to, sample a proper when your resynchronization signal again generated by n is equal to 100 or what n is. So this is a very easy hardware here. You can generate a signal. So if resynchronous is 0, it means you can, if it is 1, then you are going to take this RP here. The RP will be coming into picture where here. You are either taking an incremented, general incremented, which is rotated here, or you are going to, what I can say is generated from XP. And at the same time, when this incremented is given here to this duplicate and drop is a sort of some comparator, either to duplicate the signal or drop the signal based on whether it has got incremented or it is the same XP. It is same as that XP which normally gets incremented. So this is some, I think you can study this in detail, very difficult because it's a combination of all the things coming into picture. XP is again the ring counter output. The TM has been the timing margin taken into consideration. This transmit clock, resynchronizer, selecting between the two, which will decide either to flow control also. And this is what the plesiochronous synchronizer coming into picture. This can be done using a synchronous FIFO. So this is a FIFO of some size. You decide again what should be the size of that. The data, FIFO is filled by this data using XP, that is the right pointer, using XCLK, and when the shifting signal is high. So when you want to write shifting signal is high, and the right pointer generated will write the FIFO on X, whereas it is red using a red pointer, which is generated when the shift out is high and by the RCLK. So FIFO is filled using transmit clock and the right pointer, whereas it's red using receive clock and the read pointer. Now, this RP and XP, what we are talking, are now, there are the two brute force synchronizers and the comparators as such. So this is comparing the read pointer directly, which is by RCLK, and the brute force, that is whatever we had done, is the synchronized, XP here. And depending upon that, whether this is higher or this is higher, it gives an empty, that is FIFO is empty. Everything has been read and there is nothing in FIFO, which goes to again the control signal to start this X, which is shifting signal. So the FIFO will be filled. Similarly, here this comparator will compare the read pointer, which is synchronized by brute force synchronizer, to the clock signal, and depending upon this read pointer or this write pointer, again based on their values, compare less than, equal to, or greater than, this will generate a signal full telling that FIFO is full, the receiver hasn't read anything, and there is no need to put the data into this, and then shifting will be taken low. So this again is a control signal to fill the FIFOs and update this RP and XP, or filling the FIFO or emptying the FIFO based on the empty and full signals. I'll just go to self-time circuits in very short, 5 minutes only. Generally, self-time circuits is not clock. They do not have any clock input as such, but there will be the handshake signals like I have sent the data. Are you in a position to receive? Then data ready will be there, and if the receiver receives, it will send the acknowledge signal, and when the acknowledge signal is received, then the next data will be sent. So these handshake signals, you can use a two-phase protocol or a four-phase protocol here. That also in a minute I will tell you, but is implemented using a hardware which is called as the Muller C elements, a sort of gate, where the truth table is If both the inputs are same, either 0, 0 or 1, 1, the output will be 0. That is what was there at the inputs. Or if they are not same, then it will remember the previous. So it's a sort of either remembering or going as per the input depending upon the inputs here. So when both inputs are 0, 0, both inputs are 1, it is 1. If both inputs are different, the previous state, it will try to state the Fn plus 1 will be Fn. So this is the truth table for that. How it is implemented again at the transistor level, I am not doing. It's a simple implementation. You can see that. But this, you are using this and either using two-phase protocol between the request and acknowledge. These are the handshake signals, and it is the data going from the sender or the transmitter to the receiver. So how two-phase protocol works? The previous acknowledge, that is the receiver has given acknowledge. Now in two-phase protocol, any transition in any of the ACK or REQ represent that some new thing has happened, the event has occurred. So ACK was previously low, is going to high. It means the transmitter can, and it is received by transmitter, understand the previous data has been received and now I can put new data. So it puts a new data on the data line. Since it has put a new data on the line, it gives a signal request. Now request was initially high. Now since it has put a data, change in that level, it's done, that is, it has taken it low, and this transition in the request signal, when it's received by receiver, it understands a new data has come here, and if it is ready, it can give an acknowledge. In response to this, it gives the acknowledge signal, and then in response to acknowledge signal, it repeats. So a request is why it is two-phase protocol, because it won in two phases. This is cycle. These are the bold lines are for the transmitter, whereas this is this dotted line is for the receiver. So it is a two-phase. It doesn't wait for the signal again to return to. It doesn't get resetted to the original value. Any transition will tell either the sender or the receiver that some event has occurred and I need to take some action. So this can be implemented using Muller C elements. So this is the sender logic, whatever hardware is there. This is the receiver logic, and this is the data which sender is going to send only when it has received the acknowledged signal. So what it does is that it puts a data on the data. We'll go to that. You can see this here. That is, you have the output of this as the request signal, and the receiver is generating an acknowledged signal. So data ready signal is given by sender after keeping the data on the data bus. In response to this, Muller C element generates a request signal which goes to the receiver. Receiver takes the data and generates this acknowledge. So this is the transmitter cycle and this is the receiver cycle. Now let us see on the waveforms. So the acknowledge signal has come. So data transmitter, there will be some hardware to tell that acknowledge signal has come, but in response to this, the sender puts a data on this, and it means it has gone to 0. Okay, acknowledge signal has gone to 0, and data ready signal, let us say, is 1. Okay, now previous data signal is 1. Initially, data accepted signal has gone to 0, which has been inverted. So 1 is here, 1 is here. In response to this, when both inputs are same, the outputs will be same. So 1, it means request signal is generated. So Muller C generates a request signal. Now request signal has gone 1. So it receives the data, and data accepted signal now goes low. Goes high. It has accepted the data, so it goes high, but it is inverted, it is 0. And data ready signal also, now it takes a data. It's a sort of small pulse. It also goes low. So 0, 0 on this makes the 0, and request signal goes low. So in response to acknowledge signal, this data, it puts a new data on this, and then request signal goes low. It was initially high, then request signal was high. Now the acknowledge signal generated in response to this, it puts a new data. In response to this, request signal goes low, and at this work in a what I can say, clockwise in a step lock arrangement like this. So you can basically implement using in the 4-phase. I think I was wrongly looking into this. I was looking at the 4-phase. I had to basically had to go back here. So you can see in response to this 3, it puts the data here because it has now request has gone, they puts the data and takes the request high. So any change in the request signal will indicate the receiver that the data has changed and will work. If in case of 4-phase is basically the request going high takes a acknowledge high, but then since acknowledge has gone high, which sender will come to know, the request goes low, and in response to this, acknowledge also goes low. So there is a 4-phase. Request going high, acknowledge going high, request going low, acknowledge going low. It means a new data or the acknowledge that they will have a handshake only when a signal goes high and remains high for some time, and then again it resets to this value. This again can be implemented using 2 molar C elements, and I mean it will work in a similar fashion to give the data without using clock anywhere, and hence this is the asynchronous way using self-time circuits. No doubt the last portion I had to basically take a bit rapidly, but I think you can again see these are the things I have again taken from the literature as well as from the Daly's book. You also can refer to that. To see the waveforms, you have to basically track what exactly is happening at that level. But I think you can see that either using a single Muller C element and handshake signals where no clock is coming into picture. And I think the asynchronous mode between the processor and the interface device also can be done in an asynchronous manner if you assume how the data gets transmitted using the handshake signals in the simple IO mode and in the handshake IO mode. The similar, I think, is the logic or the philosophy has been used here. So basically, we have seen that the timing parameters of the flip-flop play a very important role in deciding the reliability of your design system designs, as well as determine at what maximum frequency the design will work. You can have for synchronizing the synchronous signal, the brute force synchronizer, but a synchronizer failure also can happen, and for that, flip-flop with lower synchronization recovery period will be a better one. Or, I mean, in that case, instead of having a pipeline of only one, if you can use a pipeline of 2, it will ensure that the signal will be synchronous. That's again extending the brute force synchronizer instead of by one pipeline flip-flop by 2 pipeline flip-flops, where the latency will be of 2 clock cycles. But you can afford it because when the data is coming in a stream manner, a latency of 2 will not matter. A periodic synchronizers, mesochronous, plesiochronous, where the delay can be, for mesochronous, delay can be in the data or can be in the clock. And we have seen very nicely how 2 register or the 3 register 3/4 synchronizer can work to synchronize the data at the receiver end. Plesiochronous synchronizer, similar to mesochronous, except that some more hardware required for the flow control, as well as for generating the RP, XP properly, and as well as for generating the resynchronization signal. The implementation of asynchronous FIFO for filling the FIFO and emptying it also will be a part of one of the components of plesiochronous synchronizers. So that also we have seen. And finally, if at all we have to work in future with the asynchronous signals, doing away with the clock where all these things will not come into picture, and then in the handshake mode, how we can make use of the Muller C element here, a gate-like structure to implement 2-phase and 4-phase protocols. In that case, the I think circuits will be more faster. And this, I mean, it's very difficult for us to see these things in FPGA because FPGA always is clocked by some clock, and implementation of these principles in FPGA also becomes a problematic. Even I am doubtful, even the EDA tools like Cadence and other also do not take into consideration the implementation of asynchronous. This is for our at present academic interest, but on the paper you can correspondingly see what could be the requirements and how you can do that. So a very important part at the system level or the block level is synchronization and synchronizers. And we have taken all cases of the two signals. And this again needs to be extended for all the signals, that is for all the data in the clock. I mean, it's very, very important that all the data are received on all the 64-bit data bus by the receiver without any bit getting corrupted. It's a very Herculean job as such, I can say, but interesting on paper. Implementation and seeing and checking and testing will be really an interesting job for if at all we work in this. Thank you very much. Any doubts as far as this is concerned? We can give 5-10 minutes for this. It's just 1:30.
Thank you, madam. Thank you very much. Anybody has any doubt?
No doubt. Okay, okay.
Yeah,
Thank you
madam, are
very
you
much.
there?
Hello?
Okay, ma'am, no doubts, I think. Just, Sneha, madam.
Yes, sir.
Thank you very much, sir, for nice memento. Very nice.
Yeah,
Actually,
madam, you want to say something?
actually, many of those you have given are there. I mean, behind my back in the previous workshops. In the
This is
previous
good. You can see it directly.
Anyway,
So,
thank you very much. It was interesting for me also to again work on all these aspects and extending my, sharing my thoughts on that, opinions, the design guidelines, and I hope that they will be useful to the faculty for training their students, and they can enter their students can enter into this high speed, low power, detailed design as era as such, or the area as such. So it's a nice COVID experience also. Putting more time on online, but this online I experienced that I do not know that how really will be effective from student point of view, and how effective will be for conducting the lectures and understanding of the students for implementation purpose and the practical purpose. No doubt, I think yesterday also I said that government has taken up this task, and they expect that within 3 years, the whole 1,000 days, they have said that every part will get fiber line, and students will be able to see that. But let it become robust and reliable, and anytime, anywhere, really should be a reality. So thank you very much,
yes,
sir.
yes.
Thank you all the
Thank you, madam.
participants for patiently listening to me. Thank you very much.
Thank you, ma'am. Thank you very much. Thanks a lot, ma'am.
Okay, thank you, sir.
Thank you, madam, for the wonderful and informative session. We really enjoyed the session.
Thank you, Priya madam. Thank you, Sneha madam. Thank you, Rathod sir. Thank you, all of the participants. Being a
Thank you,
senior, I
ma'am.
request, being a senior, maybe the senior most faculty, as far as the participants and organizers also are concerned, I
But
request,
you are the most
yes.
enthusiastic faculty, madam. You are the
No,
most enthusiastic
I
faculty.
forget about me. My days are getting over now. I only think that I should have second life to again see into details of this. So one life is not enough. But for all those who still have a career to make, I take anything you do, take it passionately. Then only your learning will be there. And looking at your passion, your students will learn, which basically are our future generation. Our entire country depends on their initiative to do something which is innovative, and they will have that motivation only after seeing you getting motivated. You become a big charge, a big capacitor, giving charge to hundreds of your students, and they will do many things for nation. You know, at present our nation is suffering very badly from all the sides. Even technology, we are using it, not developing it, no doubt. At present the efforts are there from the government, but yesterday disasters are taking place. Whether is disaster management so bad, whether our students can take part in that to do something, that is something maybe after 10 years down the line we should be better off than what we are today. And that basically is something which is depressive to me. But you will see that those things, and those will be the fruits of your efforts as on today. So I request you to take anything very passionately. There has to be something which will which will trouble you day out and day night. Thank you very much. I took this authority to give you this advice, but I think should be done. We need Maharashtra also to stand as number one as a state in country, and India in the world as such. And these are all your efforts. So I'm thankful to you for attending this. Attend all further workshops also, but have proper attendance and proper interaction with the one who is doing this with the organizer as well as the resource persons. Thank you very much. Thank you, sir, Rathod sir.
Thank you,
May I
ma'am.
leave?
Thank you.
May I leave?
Yeah.
Yeah,
Yes. Everyone, we will be meeting evening 5 o'clock, 5 to 7. Dr. Naushad's session is there, no? On layout.
Okay. I will be
Yeah.
on and off today, sir.
Okay, ma'am. No problem.
Okay. Thank you very much.
Thank you.